Close your eyes for a moment and let your mind drift. Imagine yourself stepping into a vast chamber where a great machine hums softly in the shadows. This is no ordinary device. It is a time machine, a vessel not bound by seconds or years, but capable of carrying us across eons. Tonight, we will board this vessel together. And as you listen, as your body begins to sink into the comfort of rest, allow your imagination to wander with me far beyond the reach of human memory, into a world that existed 500 million years ago. The dials turn. The machine trembles. Time begins to peel back layer after layer, like pages from an ancient book. The centuries blur, the millennia vanish. You feel civilizations disappear in reverse. Empires unravel. Cities unbuild themselves, forests retreat, and mountains wear down into flat plains. Still, we move further, until even the first humans dissolve into nothing. The mammals vanish, the dinosaurs fade, and the great forests of the Carboniferous era are swallowed by time. We continue back further still, past the first primitive land plants, past the moment when fish first developed jaws. And finally, after what feels like an eternity of reverse creation, we stop. The dials freeze at 500 million years ago. The machine falls silent. When we step outside, the Earth greets us not as the home we know, but as a strange and alien planet. The continents are unrecognizable, small and scattered, as though a giant hand has broken apart a puzzle and tossed the pieces into the sea. The land is bare, rocky, and mostly lifeless. There are no trees, no grass, not even moss carpeting the stones. The world smells different, raw mineral, untamed. The air is thick with carbon dioxide, and the oxygen, though present, exists in much lower quantities than we are used to breathing. Yet while the land seems empty, the oceans sing with hidden life. Beneath the waves, something extraordinary is happening. This is the age of the Cambrian explosion, a time when evolution was experimenting wildly, producing shapes and forms that are almost beyond imagination. The seas are full of creatures never seen before and never seen again, each stranger than the last. They dart, crawl, drift, and hunt, filling every ecological niche for the very first time. The diversity is breathtaking, a kind of biological symphony at the dawn of complex life. Picture yourself walking along one of these lifeless shores. The ground crunches under your feet, a mixture of sand, gravel, and stone, untouched by roots or greenery. The horizon is open and barren, painted with a wide sky. Above you, the sun burns a little fainter than today, its light softened by a young atmosphere, but still warm enough to keep the world alive. Clouds drift lazily overhead, carrying rains that nourish no forests, no grasslands, only bare ground. The silence is overwhelming. No birds cry out, no insects buzz, no leaves rustle. The only sounds are the crash of waves and the whisper of wind against rock. But as you approach the water's edge and gaze down into the clear blue depths, the silence breaks into a different kind of music. Here, beneath the surface, life is stirring in dazzling abundance. Swarms of trilobites crawl along the sandy seafloor, their hard exoskeletons glinting in the sunlight that filters through the shallows. Nearby, worm-like creatures burrow and tunnel, aerating the sediment in ways that would transform the ocean floor forever. Strange predators drift by, Anomalocaris with its grasping, spiny arms and circular mouth glides through the water like a living torpedo. And then there is Opabenia, with 5 eyes perched on stalks and a long proboscis extending like a claw, a creature that seems pulled straight from a dream. Everywhere you look, the oceans are alive with these alien forms. Some are armored, some are soft-bodied, some resemble modern animals faintly, while others have no direct descendants at all. They are Earth's first grand experiment in complexity, a moment when life seemed to burst forth with 1,000 ideas at once. For us, standing at the shoreline of this ancient Earth, It feels like stepping into another world entirely. What makes this time so profound is not just the creatures themselves, but the sense of possibility. 500 million years ago, the story of complex life had only just begun. Every niche was open, every opportunity untouched. There were no towering trees to shade the seas, no animals to graze, no birds to swoop down from above. Instead, the oceans were like an open canvas, waiting for life to paint itself upon it, and nature painted boldly. Let us linger here for a while. Imagine lying down on a rocky ledge, listening to the surf as it rises and falls. Your eyes trace the horizon where the sun dips slowly, painting the sky in colors not so different from our own sunsets. But as you breathe, you sense that the very air feels alien, thinner in oxygen, heavier in carbon dioxide. You would not survive long without aid, but your imagination is enough to carry you. You are a witness to a world that no human has ever truly seen. The scale of time here is humbling. 500 million years. It is a number so vast that it almost loses meaning. To put it in perspective, if human history, from the first written word to today, were a single day, then the Cambrian seas would lie millions of days before it. When you think of it this way, the human story feels like the flicker of a candle in a storm compared to the roaring fire of geological time. And yet, though distant, this ancient Earth is not irrelevant to us. The creatures swimming in these seas would, through countless generations and branching lineages, give rise to forms that shaped the future. Without them, without this explosion of life, we would not exist. Every breath you take today, every step you make on modern Earth, is rooted in what happened here in this seemingly alien ocean 500 million years ago. So, as your body grows heavier and your mind drifts closer to sleep, hold this image with you: a silent world of barren land, a sky filled with pale sunlight, and an ocean alive with strange, glittering forms. This is Earth at the dawn of complexity, a place both foreign and familiar. A place that reminds us of how deep the story of life truly runs. And this is only the beginning of our journey. For as we continue to travel through these ancient landscapes, layer by layer, we will uncover not just the history of the planet, but also the origins of the life that one day gave rise to us. Close your eyes and let's continue this voyage together. We've already stepped into the idea of traveling back 500 million years. But the deeper you allow yourself to sink into this thought, the more incredible it becomes. Think about time not in hours or years, but in the sheer immensity of millions upon millions of years, flowing like a slow, endless river. Every second you are listening now, thousands of years slip by in the vast scale of Earth's history. Human lifetimes shrink to almost nothing. Whole civilizations rise and vanish in what would be just a blink in geological terms. And as this realization deepens, you begin to feel both very small and very much a part of something timeless. Earth, 500 million years ago, was an alien place compared to the home we know today. Not alien in the sense of beings from other worlds, but alien in its landscapes. Its skies, its oceans, and the forms of life that crawled, swam, and drifted across its surface. To imagine it, we need to peel back the layers of time, like opening one ancient book after another, each revealing strange and forgotten chapters. The rocks under our feet still whisper those stories. The fossils locked inside them are frozen pages of a diary Earth never intended to write, but did nonetheless. And we, in this quiet journey tonight, are the readers. Imagine yourself drifting through these pages of deep time. First, we peel away the present, the world of cities, forests, rivers, and mountains. Then, we peel away the ice ages, the great glacial sheets that once covered much of the northern hemisphere. Peel again, and we see early humans discovering fire. Then go back further to when there were no humans at all. With every layer, the shapes of continents shift. Climates transform, and life itself morphs into something almost unrecognizable. By the time we remove hundreds of millions of years, we arrive at the Cambrian period, roughly 500 million years ago. It is a place beyond human memory, beyond myth, beyond even the oldest whispers of culture. It is pure prehistory. The continents themselves were not where we see them now. Picture Earth as a puzzle whose pieces are constantly rearranging. Back then, those puzzle pieces were clumped together in ways that made coastlines unfamiliar. Shallow seas spread across much of the land. And what little was exposed above water was barren: no grass, no trees, not even moss. Just rock, sand, and wind. The land was silent and lifeless. All the action, all the drama was happening in the oceans, and those oceans, they were bursting with a new kind of energy. 500 million years ago marks a turning point in the history of life called the Cambrian explosion. It was as if evolution suddenly discovered creativity on a grand scale. Creatures with shells, teeth, eyes, and claws appeared almost all at once in the fossil record. For billions of years before this, life had been mostly simple, single-celled organisms, algae, and some soft-bodied creatures drifting in the water. But in the Cambrian seas, everything changed. For the first time, ecosystems began to resemble something like the complexity we know today. Predator and prey, hunter and hunted, speed and defense, these dynamics suddenly mattered. Try to picture it: the seafloor alive with trilobites, creatures that looked like armored beetles crawling through the sand. Above them, strange worm-like animals burrowed and poked their heads out like cautious explorers. And among them swam some of the strangest beings evolution has ever produced: giant shrimp-like predators with spiny, grasping appendages, soft-bodied oddities with no modern relatives, and tiny creatures with spines, plates, and bizarre body plans that almost seem like experiments. Some of these experiments would last for millions of years. Others would vanish almost as quickly as they appeared, leaving only faint fossil traces behind. But before we dive fully into those alien oceans, let's pause and reflect on something important: the perspective of time itself. One of the greatest challenges in imagining Earth 500 million years ago is the scale. We can say 500 million years, but what does that really mean? Imagine stacking books, one for every year of recorded human history. The pile would be just a few thousand books tall. Now imagine needing a pile 500 million books tall to represent the time that separates us from the Cambrian period. Such numbers overwhelm the mind, and yet they are real. This was our planet, our Earth, just unimaginably older, wilder, and different. It's worth remembering, too, that the Earth itself was already ancient by that time. When we look back to 500 million years ago, we are not at the beginning. The Earth had already existed for almost 4 billion years before that point. Mountains had risen and crumbled. Oceans had formed, dried, and formed again. Continents had collided and broken apart in endless cycles of geology. Life had already endured ice ages and mass die-offs long before the Cambrian seas came alive. So, in a sense, what we are about to explore is not the beginning, but a middle chapter in an almost incomprehensibly long story. And this is where the sense of awe truly takes root. Because somewhere, hidden in those oceans, are the ancestors of everything we know. The ancestors of fish, of insects, of trees, of birds, and even of ourselves. They were small, fragile, and strange, but within their bodies lay the seeds of all future possibility. 500 million years ago, the blueprint of life as we know it was being written in the language of survival. As you relax and let these images float in your mind, imagine yourself standing on the shore of one of those shallow seas. The sky is the same sunlit blue, though the oxygen levels are not quite as high as today. The air is dry, empty of birdsong, empty of the hum of insects, empty of any scent of grass or flowers, just wind and silence. Before you, waves lap gently against bare rock. Beneath those waves lies a living world, utterly foreign yet strangely familiar in its rhythms. For every predator, there is prey. For every swimmer, there is a current. For every species, a niche. And in that balance lies the beginning of ecosystems. This is where our long journey will take us, into the seas of the Cambrian. Through the ages that followed, across shifting continents, through extinctions and rebirths, and eventually forward to the world we know today. But for now, simply let yourself drift in the realization of time's vastness. Let it remind you that Earth is not just the planet you see outside your window. It is a story of endless transformation. A story still unfolding. A story of which you are a part. Take a deep breath and let your thoughts slow down, as if the very passage of time is stretching with each inhale and exhale. You are no longer rushing through minutes and hours. Instead, you are gliding across centuries, millennia, eons. The Earth before us is not one of memory, not even one of legend, but of pure imagination guided by science. It is a world beyond the reach of any story humans have ever told. A world no eyes have seen and no mind has ever fully captured until now. In this quiet journey together, picture yourself standing on a cliff overlooking a vast ocean, 500 million years ago. The cliff is bare, a rugged slope of stone carved by winds that carry no scent of life. The air is still thin, holding less oxygen than you're used to. Breathing feels different, sharper, drier. There are no trees rising behind you, no grass brushing your ankles. Only rock, stretching as far as you can see, with perhaps a few patches of lichen clinging stubbornly to the stone-tiny pioneers of land. Life that are just beginning to claim their place. The silence is immense, as if the whole world has been waiting for something. And indeed, it has below. The sea ripples in soft shades of green and blue. But don't be fooled by the surface. It hides a kingdom more vibrant, more experimental, and more alien than any story of dragons or spirits. Beneath those waves, creatures with armored shells crawl across the seafloor. Others drift gracefully, shaped like ribbons or spiked wheels. Some have multiple eyes, gleaming like tiny lanterns in the dim underwater light. Others are nothing more than soft-bodied mysteries, pulsing gently in the currents. This is not the ocean, you know, and yet, it is the birthplace of everything to come. Let yourself float down into that water in your mind. The temperature is different, warmer in some places, cooler in others, but not yet governed by the modern rhythms of ice and seasons. Sunlight filters through the waves in dancing ribbons of gold. As you sink deeper, you begin to see movement. Trilobites, countless trilobites, marching across the seabed like little armies of armored explorers. Some dig into the sand for food, others cluster in groups as if for safety. Their many eyes catch the light, glinting like polished jewels. They are small, only a few centimeters long, but they rule these oceans, their shapes endlessly repeating across the world. Look closer, and stranger forms appear. A creature with a long, tubular body floats by, waving delicate, feathery limbs to filter food from the water. Another darts quickly past, with spiny claws snapping one of the earliest predators. Its name, given millions of years later by human scientists, is Anomalocaris, the unusual shrimp. But here, in its time, it is no curiosity. It is a fearsome hunter, gliding smoothly with powerful fins, eyes as large as marbles scanning for prey. For the trilobites crawling below, it is a nightmare in motion. And yet, these seas are not ruled by fear alone. They are filled with endless experiments of life. Some creatures look like armored slugs. Others are shaped like flat discs that flap gently, almost like paper kites. Some are tiny, almost invisible, drifting like dust motes in a sunbeam. And yet, they are the foundation of the food chain, the beginning of everything. The ocean floor itself is alive with burrows, trails, and tiny signs of activity, as though the very sand is being written upon by the movements of these early animals. It is here, in these countless small stories, that ecosystems are born. Now step back again, in your imagination, to the wider planet. Above the seas, the continents are bare, quiet, waiting. The winds whistle over stone plains and jagged hills. Rivers carve through empty valleys with no trees to shade them, no roots to hold their banks. The moon rises and sets over a world of silence, illuminating a surface untouched by forests, flowers, or animals. If you could stand here long enough, you would see the continents slowly drift, pulled by forces deep within the earth on endless. Patient reshaping of the surface that continues even today. But at this moment in history, the land is still in waiting, a stage not yet filled. And this is the image to hold on to as we begin our long exploration together. Earth as an unfinished masterpiece. The seas filled with new and daring forms of life. The land quiet but full of potential. The air thin but slowly growing richer, setting the stage for the future. 500 million years ago, the story of complex life was just beginning, and the chapters ahead would be more astonishing than anything before. As you listen, you may find yourself drifting not just in thought, but perhaps closer to sleep. That is all right. This story is meant to carry you gently, like a current in the sea, flowing without urgency. Whether you remain fully awake, or whether your mind begins to wander and dream, the journey continues. Earth's story is vast enough to hold you, to soothe you, and to remind you of how extraordinary existence truly is. Remember, too, that in these early oceans, hidden among all the strange and alien creatures, are the seeds of us. Not us as humans, not even as mammals, not even as vertebrates yet, but the very beginnings of complexity, of structure, of possibility. Evolution was writing its first great symphony. And though the notes were unfamiliar, the melody would eventually give rise to all the wonders of life, the forests, the birds, the whales, the people. And so, as you let yourself rest, know that this long story is your story too. You are connected to the trilobite, to the worm, to the drifting plankton. You are a chapter in a book that began long before memory, long before history, long before even the whisper of myth. So let's begin, together with patience and wonder. Ahead of us lie oceans that glow with ancient life, continents that will shift and break, creatures that will rise and vanish, extinctions that will wipe the slate clean, and rebirths that will make the world new again. This is Earth ever-changing, ever beautiful, and always surprising. This is the journey we take, across time, across imagination, into the heart of our planet's deepest past. When we look at the Earth today, we see a planet that feels solid and permanent. Mountains seem eternal, continents appear fixed, and coastlines look as though they have always been where they are. But this sense of permanence is an illusion. Beneath the calmness of landscapes lies a restless engine, one that has never stopped moving, never stopped reshaping the face of the planet. To truly understand the Earth 500 million years ago, we must first understand this engine, the hidden machinery of geology and tectonics. Close your eyes for a moment and imagine the Earth as a living organism. Its crust, the part we walk upon, is like skin-thin, fragile, and ever-renewing. Beneath that skin lies the mantle, a slow-moving river of rock so hot that it flows like syrup over unimaginable spans of time. And beneath that mantle lies the core, a ball of molten and solid metal that churns with energy. It is this energy rising from the deep that drives the tectonic plates, the great slabs of rock that drift across the surface like ice flows on a restless sea. Now, shift your perspective to 500 million years ago. The continents did not resemble the familiar shapes of today. There was no North America, no Europe, no Africa in their modern outlines. Instead, the landmasses were clustered in strange configurations, their borders drawn in ways we would not recognize. Some of these continents were small, others vast. They were scattered across the globe like pieces of a jigsaw puzzle, slowly inching toward and away from each other. One of the great landmasses of this time was Gondwana, a supercontinent that stretched across the southern hemisphere. Gondwana included what would one day become South America, Africa, Antarctica, Australia, and the Indian subcontinent. Imagine this giant continent, barren and silent, much of it lying close to the South Pole. Its coasts were lined by shallow seas, rich with early marine life, while its interiors remained largely lifeless. A desert of rock and sand waiting for plants to arrive millions of years later. Elsewhere, other continents drifted. Laurentia, which would one day form the heart of North America, floated closer to the equator, bathed in warm sunlight. Baltica, the seed of modern Europe, and Siberia, smaller but significant, also lay scattered across the globe. These landmasses were not static. They moved slowly, a few centimeters each year, carried by the shifting mantle beneath them. Over millions of years, these small movements added up, bringing continents together into collisions or pulling them apart into new oceans. The Earth's surface, then, was a dynamic stage of shifting plates. And with movement came drama. Where plates collided, mountains began to rise. Where they pulled apart, oceans spread wider, their floors paved with fresh volcanic rock. Along the edges of continents, where plates slid beneath one another, volcanoes erupted and earthquakes shook the land. Though no human eyes witnessed these events, their effects were profound. The arrangement of continents shaped the flow of oceans and winds, and in turn, these shaped the climates of the world and the paths of life's evolution. Think of Gondwana. Stretched across the south, its sheer size altering currents that swept around the planet. Think of Laurentia, near the equator, its warm, shallow seas providing havens for trilobites, brachiopods, and countless other Cambrian creatures. These environments were not just backdrops for life, they were catalysts, pushing evolution forward by creating new habitats, new challenges, and new opportunities now. Let's take a closer look beneath the surface. The crust of the Earth is not a single unbroken shell. It is cracked into plates, each moving at its own pace. These plates rest on the asthenosphere, a layer of partially molten rock that shifts slowly like thick dough under pressure. This movement, though invisible in the span of a human lifetime, is unstoppable across geological time. Continents that appear steady are in fact drifting, and oceans that seem endless are opening and closing like the slowest of breaths. 500 million years ago, this tectonic breath was in a different rhythm. Oceans like the Iapetus Ocean separated Laurentia from Baltica and Gondwana. Its waves lapped against ancient shores, carrying nutrients and life, while deep below, spreading ridges pushed the ocean wider year by year. Eventually, these plates would move closer, closing the Iapetus Ocean and giving rise to mountain ranges. But for now, in the Cambrian world, the ocean was vast. A silent expanse dividing the continents. A reminder that Earth's surface is always in motion. It is easy to think of geology as dry or distant, just rocks and plates. But listen closely, and you will realize it is a story of movement, of transformation, of a planet that never sleeps. The continents were rafts, drifting slowly across a sea of molten rock. Volcanoes erupted, spilling new land into existence. Earthquakes split the silence with sudden violence, reminders of the forces lurking below. And though the land above was still mostly barren, its shape and position were already writing the destiny of the life hidden in the oceans. When you imagine Earth 500 million years ago, don't just think of the seas filled with strange creatures. Imagine the ground beneath those seas. Imagine continents grinding against each other, tearing apart, reforming. Imagine mountains rising only to erode into the waves, sediments carried back into the deep, buried, and reborn as stone. The cycle of creation and destruction, already ancient, was in full motion. It is this restless, unseen machinery that has always shaped Earth. And it was no less powerful in the Cambrian Age. As you let this vision settle in your mind, remember, the planet beneath your feet tonight is still alive with this same energy. The mountains you see today, the valleys, the coasts, they are just temporary expressions of deeper forces. 500 million years ago, the shapes were different, but the principle was the same. Earth's crust floated, shifted, and collided, sculpting the world in silence and fire. Now that we have seen the restless continents of 500 million years ago, let us turn our attention to the waters that separated them, and to the fiery forces that burned beneath. For the oceans of the Cambrian world were not just empty spaces between drifting lands. They were the heartbeat of the planet, pulsing with energy, shaping climate, and cradling the story of life's earliest complexity. And beneath those oceans, unseen but never absent, volcanoes whispered their power, each eruption rewriting the map of Earth in fire and ash. Imagine standing in your mind on the edge of Laurentia, the ancient heart of what would one day become North America. Before you stretches the Iapetus Ocean, a vast expanse of water shimmering beneath the Cambrian sun. Its name, chosen by scientists millions of years later, recalls Iapetus, the titan of Greek myth. But in this time, it is no myth at all. It is real, immense, and alive. Gentle waves lap against the shore, but far out to sea, currents move with a hidden purpose, carrying warmth, nutrients, and life across the globe. The Iapetus Ocean was more than a body of water. It was a pathway. It connected the shallow coastal shelves, where trilobites scuttled and early corals built their tiny colonies, to the deep. Dark realms where strange, soft-bodied creatures drifted in silence. Its currents shaped climates, determining which coasts were warm and welcoming, and which were cold and barren. And in time, its closing would drive continents together, sparking the rise of mountains and the reshaping of the world. But in this moment, during the Cambrian period, it was wide open and filled with possibility. Now, let us sink below those waves and journey to the ocean floor. Here, the Earth itself is creating new crust at mid-ocean ridges. Long chains of undersea volcanoes where molten rock pushes upward from the mantle, splitting the plates apart. Imagine walking along the crest of such a ridge, though of course no feet had yet touched it. You would see glowing lava erupting in slow fountains, cooling quickly in the water to form black, glassy rock. The ridge would stretch for thousands of kilometers, a fiery seam unzipping the ocean floor. Around these ridges, hydrothermal vents spewed scalding water rich with minerals. Black smoke curled upward in columns, carrying chemicals that would nourish entire communities of early life. Though complex vent ecosystems like those of today were still in their infancy. These places hinted at the deep connection between geology and biology. Life was not separate from the Earth, was entwined with it, shaped by every pulse of molten rock and every shift of the plates. Beyond the ridges lay volcanic islands, some rising above the waves, others buried beneath them. These islands were born in eruptions that could last for centuries, each new flow of lava adding to their mass. In the Cambrian seas, such islands might have been barren, no trees, no birds, no green slopes. Instead, they were raw, black landscapes of cooling rock, battered by waves and winds, awaiting the slow colonization of simple life. Yet even in their starkness, they played a role, interrupting currents, redirecting winds, and setting the stage for future ecosystems. Now let us rise above the waves again and consider the sky. Volcanoes did not only shape the land and sea. With each eruption, they hurled gases into the atmosphere: carbon dioxide, sulfur, water vapor. These emissions influenced climate, sometimes warming the Earth, sometimes cooling it. Imagine a Cambrian sky tinted with the haze of distant eruptions, The sun softened behind thin veils of volcanic particles. The atmosphere of this age was still different from today, holding less oxygen, more carbon dioxide. The breath of volcanoes contributed to this balance, slowly altering the air that one day would support forests, animals, and us. Then was a system of constant exchange. Plates moved, opening oceans or closing them. Volcanoes erupted, reshaping the land and feeding the air. Currents shifted, carrying warmth to one coast and chill to another. Nothing was still. Nothing was fixed. And yet, from this constant restlessness, a kind of order emerged. The climate stabilized enough for life to flourish in shallow seas. Nutrients cycled through the water, fertilized by volcanic ash and river sediments. The very instability of the Earth became the foundation of life's stability. Think again of Gondwana, vast and silent in the south. Its position near the pole influenced currents that swept around the globe. Ice may have formed along its southern edges during colder intervals, influencing sea levels worldwide. Meanwhile, Laurentia basked in tropical warmth, its shallow seas teeming with trilobites, sponges, and brachiopods. These contrasts were not accidents. They were written by tectonics, by the placement of continents, by the depths of oceans, by the fire of volcanoes beneath the crust. In this way, geology was not background. It was author. Every collision of plates, every eruption, every shift of the ocean floor wrote a new chapter in the story of life. Without the restless crust, there would be no shifting climates, no evolving environments, no endless experimentation of species. The Earth's pulse, its tectonic and volcanic rhythms, was the metronome to which life composed its symphony. And so, as you drift deeper into thought, let this vision surround you. Picture the wide Iapetus Ocean glinting under an ancient sun. Picture volcanic ridges glowing faintly in the deep, their vents exhaling warmth into the darkness. Picture islands rising from the waves still steaming from their birth. And picture, above it all, the slow drift of continents, patient and unstoppable. Moving to a rhythm older than memory, the Earth you walk upon tonight is built from these same processes. The continents under your feet were once volcanic islands, once sediments at the bottom of ancient seas, once mountain peaks eroded to sand. 500 million years ago, the shapes were different, but the dance was the same. Oceans opened, volcanoes erupted, plates shifted. It is a dance without end, and one that continues, unseen, even as you rest and dream. As we drift further into the ancient world, it is worth remembering that Earth's surface was not a silent landscape. Beneath every mountain chain, beneath every shallow sea, there was an engine of constant movement. The slow churn of mantle currents, the grinding of tectonic plates, and the recycling of crust through subduction were all orchestrating the architecture of the planet. And while we often imagine the Cambrian Earth as static, frozen in time, it was anything but. In the southern hemisphere, the supercontinent Gondwana continued to dominate. Its sheer size influenced global climates and currents, but it also revealed fault lines along which tomorrow's continents would eventually break. At its northern edges, smaller plates like Laurentia and Baltica were not passive spectators. They were wandering, colliding, and slowly preparing the stage for continental configurations far in the future. Picture Laurentia again, a massive block that would one day form the backbone of North America. Around 500 million years ago, Laurentia floated near the equator. Warm, shallow seas flooded its margins, creating platforms of carbonate deposits that would one day harden into limestone cliffs. Yet deep beneath, tectonic pressures were already forming sutures, invisible cracks that foreshadowed dramatic events in the coming Paleozoic. These shifting plates carried volcanic arcs and microcontinents toward Laurentia, sparks of geology that would later ignite Origenist mountain-building episodes so immense they would sculpt vast ranges. Meanwhile, Avalonia, a smaller landmass, was separating from Gondwana. Imagine this fragment breaking away slowly over millions of years, carried northward across the Iapetus Ocean. What seems like an eternity to us was, for the planet, the blink of an eye. Avalonia's slow voyage would eventually lead to its collision with Baltica and Laurentia, giving rise to the early Appalachian Mountains. But in the Cambrian, this was still a distant story, hidden in the subtle rearrangements of tectonic boundaries. The oceans themselves tell another story. Mid-ocean ridges stitched across the seafloor, releasing molten rock that spread outward like conveyor belts. Hydrothermal vents spewed mineral-rich fluids, creating hotspots of chemistry that nourished early animal communities. These ridges not only reshaped the ocean basins, but also controlled sea levels. At times of rapid spreading, the ridges pushed up higher, displacing water onto the continents. This is why the Cambrian world was so often drowned beneath shallow seas. Plate tectonics was literally lifting the ocean floors. Let us not forget subduction zones, where one plate dove beneath another. These boundaries generated volcanic arcs, chains of fiery peaks that occasionally pierced the surface. Imagine a long, curving chain of volcanic islands in the Iapetus Ocean, glowing with molten eruptions, ash clouds drifting into the sky, and lava flows solidifying against waves. To the tiny marine creatures of the Cambrian, these islands were monumental obstacles, rocky barriers in an otherwise vast, liquid world. One remarkable effect of tectonics was the rearrangement of climate zones. Since the continents sat at different latitudes than today, wind and ocean currents had unusual patterns. Equatorial regions experienced vast, warm currents, circulating nutrients and heat, while polar regions were barren and cold. But because Gondwana was so large and stretched toward the pole, it fostered desert conditions inland, even as its coasts were bathed in shallow seas. The contrast between arid interiors and flooded continental shelves made Gondwana a continent of extremes. If you were to stand on the coast of Gondwana 500 million years ago, the world might seem oddly quiet. The landscape would be flat, broken by eroded hills and broad plains. There were no towering forests, no flowering plants, no carpets of green. But at your feet, waves washed over tidal flats, where tectonic activity had created basins filled with shallow, nutrient-rich water. Stromatolic scalonese of cyanobacteria built layered mounds in these waters, recording the rhythm of tides. And deep offshore, the tectonic basins hosted the first complex animal ecosystems. Hidden from the land above. Over the course of millions of years, tectonic shifts also influenced sea chemistry. When continents rifted apart, they exposed fresh rock that weathered into the oceans, delivering minerals like calcium and phosphorus. These nutrients enriched marine ecosystems, fueling the Cambrian explosion. It is not an exaggeration to say that without tectonics, life as we know it might never have diversified so dramatically. The deep link between moving plates and living creatures was already being written into Earth's history. Yet, despite all this motion, to the human imagination, the Cambrian world might feel eerily still. No sound of birds, no rustling leaves, no animal footsteps across soil. The only music was the low thunder of volcanic eruptions, the hiss of steam rising from vents, the crash of waves against volcanic islands, and a long silence of the wind across bare rock. And all the while, tectonic forces continued their invisible work, sculpting the skeleton of the planet, preparing for the ages to come. The story of Earth 500 million years ago is not only about fossils and seas, but about deep processes that we rarely sense in our modern lives. To imagine the Cambrian fully, we must picture not only trilobites crawling across seabeds, but also continents drifting like vast rafts, volcanic arcs erupting in chains, oceans rising and falling with the tempo of spreading ridges. It was a planet alive in every sense alive, with both geology and biology, each shaping the other in ways that would echo across deep time. As we leave this chapter, We hold a portrait of Earth not as a static ball of rock, but as a breathing, restless system. Gondwana, Laurentia, Baltica, Avalonia, drifting, colliding, breaking, and fusing. The crust itself was a living stage, shifting under the weight of time. And though no human eye could have seen it, every movement of those plates was setting the stage for the planet we now call home. As we drift further into the Cambrian world, it becomes clear that Earth's climate was not uniform, but a delicate balance of zones, rhythms, and patterns, shaped by the positions of continents, the configuration of oceans, and the invisible currents of the atmosphere. Seasons existed, though perhaps very differently from the ones we know today. The tilt of Earth's axis still guided the flow of sunlight across the globe, giving rise to periods of warmth and relative coolness, and subtly dictating the pace of life in the shallow seas and coastal regions. Imagine a year passing over Laurentia, positioned near the equator. The sun circles high in the sky, bathing the shallow continental shelves in intense, almost constant light. The shallow waters warm steadily, encouraging plankton blooms and providing perfect conditions for trilobites and brachiopods to thrive. Storms occasionally sweep across these regions, driven by the interplay of warm surface waters and cooler deep currents, shaking up the seas, redistributing nutrients, and reminding life that even in a seemingly gentle world, there is movement and change. Contrast this with the southern supercontinent, Gondwana, sprawling toward the South Pole. Its vast interior remained largely arid, with deserts extending for hundreds of kilometers. Rainfall was sparse, seasonal, and unpredictable. Coastal margins, however, experienced a gentler, more consistent wet season, where shallow tidal flats flooded regularly, creating habitable zones for microbial mats and the earliest small animals. Seasonal fluctuations in temperature and water levels shaped not only ecosystems, but also the deposition of sediments, slowly building layers of rock that record these rhythms for hundreds of millions of years. Wind patterns, too, were influenced by both geography and rotation. Trade winds blew steadily in tropical regions, moving warm air from east to west, while polar winds carried cooler air toward the mid-latitudes. In some areas, these converging currents generated storms relatively small by today's standards, yet powerful enough to churn the shallow seas and redistribute nutrients across continental shelves. Imagine standing in the mind's eye at the edge of an ancient coastline, feeling the soft gust of wind brushing over tidal flats, smelling the faint minerals carried from faraway lands. The Earth, though vast and seemingly calm, pulses quietly with energy. Ocean currents and climate were deeply intertwined. Warm equatorial waters moved slowly toward the poles, while cold polar currents drifted toward the equator, creating zones of mixing. Where these currents converged, planktonic life thrived, feeding small predators and supporting increasingly complex food webs. In the Cambrian world, these currents were more than water movement, they were lifelines, connecting distant ecosystems, shaping where species could survive, and influencing the very chemistry of the oceans. Even slight changes in wind or sea temperature could ripple across the globe, subtly altering habitats and migration patterns. Volcanic activity played a critical role in this climatic choreography. Eruptions along tectonic boundaries injected gases into the atmosphere, temporarily cooling regions by reflecting sunlight, or warming them through the long-term accumulation of greenhouse gases like carbon dioxide. Some eruptions released aerosols that circled the globe, softening the sun's intensity and producing vivid sunsets for creatures beneath. The atmosphere and crust were in constant conversation, exchanging heat, particles, and energy, shaping both the weather and the conditions for life. Rainfall, while often gentle, could vary dramatically depending on location and season. Tropical shallow seas experienced consistent precipitation, nourishing microbial communities and transporting minerals into the ocean. Meanwhile, desert interiors of Gondwana saw sporadic storms, sometimes violent, leaving behind temporary rivers and floodplains. These episodic events, though rare, were critical for distributing nutrients, shaping early sediments, and influencing the development of ecosystems across the supercontinent. Even the daily rhythms of day and night contributed to climate effects. The sun's warmth drove evaporation, cloud formation, and gentle breezes. Nighttime cooling allowed shallow waters to release stored heat back into the atmosphere. The cycle of heating and cooling, while subtle, created microclimates along coastlines, tidal flats, and island shores. These microclimates provided niches for early life forms, promoting diversity in otherwise uniform shallow seas. 500 million years ago, Earth's atmosphere also contained elements we might find unusual today. Methane, for example, was more abundant, subtly warming the planet and interacting with other gases to create a mild greenhouse effect. Nitrogen dominated the air, as it does now, providing a steady, inert background. Oxygen, while present, had not yet reached the concentrations necessary to support large terrestrial life, limiting activity to the shallow seas. And yet, despite these differences, the atmosphere functioned as a stable, predictable system for marine life, providing warmth, circulation, and the gentle rhythms that allowed the Cambrian explosion to unfold. In thinking about these patterns, it's important to recognize that climate was never uniform and life adapted accordingly. Some regions were hot, others cold. Some shallow seas teemed with activity, while others remained quiet, almost sterile. Currents, winds, and rainfall guided the placement of organisms, while tectonic movements gradually shifted continents into new zones of sunlight, rainfall, and ocean circulation. The story of life is inseparable from the story of climate, and the Cambrian world reminds us of this intimate connection. Imagine drifting gently over these ancient lands and seas, feeling the pulse of seasons, the whisper of winds, the warmth of sunlight, and the cool touch of water. The Earth itself seems to breathe slowly, rhythmically, almost imperceptibly. 500 million years ago, the planet was alive not only with geological movement, but with the subtle, pervasive rhythms of climate. These forces shaped the very stage upon which early animals, algae, and microbial mats played out the first acts of complex life. And as you listen, let yourself relax into this vision. Feel the cadence of ancient winds, the steady warmth of tropical seas, the soft murmur of distant storms, and the slow, deliberate movement of continents beneath. The atmosphere and climate of the Cambrian world were patient teachers, shaping life not through sudden events, but through continuous, gentle influence. They remind us that Earth, even in its oldest moments, was a living, breathing system full of surprises and quiet power, guiding the future of life across unimaginable spans of time. As we move into the final section of this chapter, let us lift our gaze fully to the Cambrian sky, imagining it not as empty space above, but as a living, dynamic system. The air that enveloped Earth 500 million years ago was thick with potential. Carbon dioxide levels were high, enough to keep the planet warm, while oxygen levels were still climbing, far lower than today, shaping where and how life could exist. Methane, water vapor, and trace gases added complexity, subtly influencing temperature and precipitation patterns. Picture standing on a calm Cambrian shoreline, the wind carrying the faint scent of mineral-rich water and distant volcanic smoke. The sun glimmers pale in the sky, filtered by a thinner ozone layer than ours. Clouds drift lazily, occasionally thickening into soft storms that release gentle showers onto shallow tidal flats. These rains are not violent, but purposeful, slowly nourishing microbial mats, trilobite habitats, and the algae that sustain early marine food webs. The atmosphere and its gases are silent architects, governing the distribution of heat, the movement of winds, and the chemistry of the seas below. Let us consider oxygen, the very gas we take for granted. During the Cambrian, oxygen levels were lower than today, likely around 15 to 18% compared to the 21% we breathe now. This meant that large, land-dwelling animals could not yet exist, and even marine life was constrained in size and activity. Oxygen-rich zones were often shallow and near continental shelves, where waves and currents mixed the water, allowing creatures to flourish. In deeper waters or stagnant basins, oxygen was scarce, shaping early ecosystems in ways we can still detect in the fossil record. Carbon dioxide, on the other hand, was plentiful. As tectonic plates moved, volcanism released enormous amounts of CO into the atmosphere, creating a natural greenhouse effect. This warmth kept shallow seas comfortable for early life, even in regions that might otherwise have been too cold. Yet the presence of CO was a delicate balance. Small shifts could cause climatic swings, sometimes warming the planet further. Other times, subtly cooling it through weathering processes that removed carbon from the atmosphere. The interplay of greenhouse gases, volcanic activity, and ocean circulation created a stable yet dynamic climate system, perfectly tuned to the Cambrian world. Methane also played a quiet role, acting as a minor greenhouse gas, trapping heat and interacting with other gases to stabilize the climate. Water vapor, cycling continuously through evaporation and rainfall, drove the gentle rhythms of weather. Clouds formed, drifted, and dissolved in patterns dictated by ocean currents and wind belts. These patterns shaped the distribution of early life, guiding where nutrient-rich waters would encourage flourishing ecosystems and where barren zones might persist. Let us now imagine a full day over the Cambrian seas. Morning sunlight warms the shallow waters, causing gentle currents to rise. By midday, clouds begin to form, responding to the interplay of warm surface water and cooler air aloft. Afternoon breezes push these clouds across continental shelves, delivering soft showers that nourish tidal flats and deliver nutrients from eroded rocks into the water. Evening arrives with a soft glow, the sky painted in subtle oranges and purples as the sun dips below the horizon. Each day repeats this rhythm, a quiet, patient cycle that sustains life in its earliest complex forms. Over longer timescales, the Cambrian sky was shaped by interactions between continents, oceans, and the atmosphere. As supercontinents shifted, the positions of mountain ranges, ridges, and basins altered wind patterns, storm tracks, and precipitation zones. These long-term changes affected sea levels and sediment deposition, influencing marine habitats and the evolution of early animals. The Earth's climate was therefore a mosaic, parts calm, parts turbulent, parts nutrient-rich, parts barren, each zone defined by the subtle forces of air and water working together over millions of years. Even volcanic eruptions influenced the Cambrian sky. When a volcano erupted, ash and gases rose high into the atmosphere, sometimes circling the globe and temporarily altering climate patterns. Sulfur dioxide formed reflective aerosols, cooling regions and creating temporary shifts in weather, while carbon dioxide slowly accumulated over time, promoting long-term warmth. These effects remind us that the Cambrian atmosphere was not passive. It responded to geological events and, in turn, shaped the environment for life to flourish or retreat. Consider the interconnectedness of all these elements. Air, water, and land were in continuous dialogue. Oxygen levels guided where marine creatures could thrive. Carbon dioxide and methane moderated global temperatures. Winds and storms moved nutrients, redistributed heat, and created microclimates. The Cambrian sky, though invisible in many ways, was as influential as the continents themselves. It was the breath of the planet, steady, patient, and sustaining life over the grand expanse of time. Finally, let us think about the legacy of this ancient atmosphere. Though oxygen was low and some gases were far more abundant than today, these conditions laid the groundwork for the future. They allowed complex life to diversify, for ecosystems to expand across shallow seas, and for new evolutionary pathways to emerge. The Cambrian sky was not just air. It was a crucible shaping the chemistry of oceans, the dynamics of weather, and the possibilities of life itself. As you relax into this vision, feel the rhythm of ancient winds, the gentle warmth of sunlit waters, and the slow dance of gases that circulated invisibly around the globe. The Cambrian atmosphere was alive, patient, and infinitely intricate, a silent guardian and nurturer of life. And as you breathe slowly, imagine joining in that rhythm, connected, if only in thought, to the planet as it existed 500 million years ago. Its sky alive with unseen forces, guiding life in ways both subtle and profound. Imagine floating above the Cambrian oceans 500 million years ago. The water stretches endlessly beneath you, a vast and calm expanse of blue-green, shimmering under the sun, filtered by an atmosphere rich in carbon dioxide and faint in oxygen. These oceans, shallow near continental shelves and deeper toward ancient trenches, were the stage for one of Earth's most profound moments, the Cambrian explosion, a sudden, remarkable diversification of complex life. As you drift over the shallow continental shelves, notice the subtle textures of the seabed. Fine sediments ripple with faint currents, forming gentle undulations. Here, life is beginning to organize itself into recognizable communities. Tiny organisms, previously microscopic, are now forming shells and exoskeletons, visible even to the unaided eye. These early arthropods and mollusks move slowly along the seafloor, searching for food, leaving trails behind them that will one day fossilize and tell the story of their lives. The Cambrian oceans were alive with activity, but not in the noisy, chaotic sense we might imagine. Life moved at a measured pace, each organism responding to subtle gradients of light, temperature, and nutrients. Sponges, simple yet efficient, anchored themselves to the seabed, filtering water to gather microscopic prey. Trilobites, with their segmented bodies and articulated limbs, scuttled across the sand, exploring the contours of tidal flats. Brachiopods clung to rocks, their hard shells a quiet testament to the evolutionary innovations of the time. Above the seafloor, currents carried nutrients from deeper waters to the shallows. These currents acted like invisible conveyor belts, dispersing food and fostering diversity. In some regions, dense blooms of plankton drifted lazily with the tide, filter-feeding organisms below. Predatory creatures were beginning to emerge, small yet significant. Their presence set the stage for a new ecological arms race, one that would drive rapid evolutionary change and contribute to the explosive diversification of the Cambrian seas. The Cambrian explosion was remarkable, not only for the number of new species, but for the variety of body plans that appeared. Consider the development of hard part shells, spines, and exoskeletons that allowed creatures to defend themselves, explore new niches, and leave a lasting imprint on the fossil record. Before this period, life had been soft-bodied and ephemeral. Now, with mineralized skeletons, organisms could interact with their environment in more complex ways, altering predator-prey dynamics and reshaping marine ecosystems. Vast communities of early animals created complex habitats. Sponge fields filtered water, leaving behind nutrient-rich patches that supported other organisms. Burrowing animals churned the sediment, oxygenating the substrate and opening new ecological niches. These interactions were subtle, almost invisible, yet they laid the foundation for modern marine ecosystems. Even without forests, coral reefs, or large predators, the Cambrian oceans were bustling with life, organized into a delicate, interdependent web. If you focus closely on the seabed, you might notice the earliest traces of behavioral complexity. Some trilobites display evidence of coordinated movement or grazing patterns. Burrows suggest sheltering strategies and avoidance of predators. tiny predators probe the soft sediment, hunting smaller animals or scavenging. Each movement, each interaction is part of a grand evolutionary experiment. A long-term game of adaptation and survival. Played out slowly over thousands of years, light played a critical role in shaping Cambrian marine life. In shallow seas, sunlight penetrated to the seabed, supporting photosynthetic microbial mats and algae. These primary producers formed the base of the food chain, sustaining the first complex food webs. Deeper waters, cooler and darker, were inhabited by fewer creatures but still harbored important innovations, including filter feeders and early predators capable of sensing subtle vibrations. This vertical stratification of life's sunlit shallows versus dim depths added yet another layer of complexity to Cambrian ecosystems. The ocean chemistry of this period also facilitated the explosion of life. Nutrient-rich waters, supplemented by the slow erosion of continents and volcanic activity, provided an abundant supply of minerals. Calcium, phosphate, and silica enabled the formation of hard parts, supporting new body structures. Oxygen levels, though modest compared to today, were sufficient in shallow, well-mixed waters to sustain active, mobile creatures. It was a delicate balance, a combination of chemistry, circulation, and light, creating ideal conditions for rapid diversification, even in this early world. The concept of predator and prey was beginning to emerge. Small predators prowled the seafloor, sensing vibrations, using spines, claws, or specialized appendages to capture unsuspecting prey. The prey, in turn, developed defensive adaptations, hard shells, spines, and burrowing behaviors. This evolutionary arms race accelerated innovation, driving morphological diversity at a pace unprecedented in Earth's history. The Cambrian explosion was not merely a period of increased species count, it was the awakening of ecological complexity. As we rise above the waves, we can observe the subtle interconnectedness of the oceans. Currents, sediment flows, nutrient cycles, and the distribution of life were intimately tied to climate, tides, and the arrangement of continents. Every organism, from the smallest trilobite to the filter-feeding sponge, depended on these factors for survival. The Cambrian seas were a world of subtle motion, patient yet dynamic, an intricate system of energy, matter, and life that set the stage for all future oceans. And so, as you let this vision settle, imagine drifting quietly over the Cambrian Ocean. See the interplay of light and water, the slow shuffle of early animals, the bloom of microbial mats, the swirl of nutrient-rich currents. Listen not with your ears, but with your imagination, to the gentle rhythms of life emerging for the first time in recognizable form. The Cambrian explosion is not a single dramatic event, but a patient unfolding, a symphony of evolution, geology, and climate orchestrated over millions of years. As we continue our journey through the Cambrian seas, we encounter a world becoming increasingly intricate. Life is no longer a passive collection of simple creatures. It is now a stage of interaction, competition, and adaptation. Predators have begun to emerge, and with them, the behaviors of prey evolve in response. These dynamics create a delicate balance that drives the evolution of diversity, shaping the Cambrian explosion in profound ways. Imagine a trilobite moving slowly across the sandy seafloor. Its segmented body allows for flexibility, its compound eyes scanning for threats. Above, a small predator worm-like creature with spiny appendages slides silently through the sediment, hunting. The trilobite senses vibrations in the water, responding with a defensive curl or rapid scuttle to avoid capture. This predator-prey interaction, seemingly simple, acts off a cascade of evolutionary pressures, favoring agility, protective armor, and sensory adaptations. Every movement contributes to the refinement of life forms, subtly pushing evolution forward. Predation was not limited to mobile hunters. Filter-feeding predators lurking in shallow waters, could exploit plankton-rich currents, capturing tiny organisms in specialized appendages. This forced prey species to develop strategies for survival, from burrowing beneath the sediment to forming protective shells. The early seas became a laboratory of survival, where natural selection sculpted morphology, behavior, and ecological relationships. The rise of predation introduced the concept of ecological niches in earnest. Some creatures specialized in grazing microbial mats, others scavenged detritus, and some became active hunters. This diversification of lifestyle fostered complexity, allowing multiple species to coexist in the same habitats without directly competing for every resource. The Cambrian oceans, once uniform in structure, became a patchwork of microenvironments, each with unique communities shaped by food availability, water chemistry, and predator-prey dynamics. Sponges, though stationary, were part of this intricate web. By filtering water for food, they not only nourished themselves but also helped recycle nutrients back into the environment, indirectly supporting other organisms. Burrowing animals churned sediments, oxygenating the seabed and exposing hidden food sources. These subtle behaviors created feedback loops, enriching ecosystems and facilitating the growth of increasingly complex life forms. Even creatures that seem simple by modern standards played essential roles in the Cambrian seas. Emergent ecological networks, movement in the oceans created new evolutionary pressures. Swimming predators, though small, introduced the need for escape strategies. Hard shells, flexible spines, and rapid reflexes became critical traits for survival. Organisms that could sense water vibrations, detect shadows, or respond to chemical cues gained advantages. This sensory evolution, though invisible to the human eye, marked a profound shift in the capabilities of life. Cambrian creatures were no longer mere passive residents of the seas. They were participants in a dynamic, interactive world. The interplay of currents and tides also shaped life. Shallow continental shelves were often bathed in nutrient-rich waters, promoting dense communities of algae and plankton. These areas became hotspots for growth, reproduction, and competition. Predators patrolled these regions while prey species developed complex defenses. Deeper waters, cooler and more stable, provided refuge for slower-moving, oxygen-tolerant creatures. The stratification of habitats along vertical and horizontal gradients fostered biodiversity, supporting a wide range of body plans, feeding strategies, and reproductive adaptations. Interestingly, the Cambrian oceans also show early examples of social behavior and coordinated movement. Fossil evidence suggests that some trilobites traveled in groups, possibly as a defense mechanism against predators. Burrowing patterns sometimes align, hinting at indirect communication or shared resource use. These early forms of behavioral sophistication hint at the deep-rooted origins of sociality, strategy, and environmental awareness in animal life. The Cambrian explosion, therefore, is not just a story of new species, but of new ways of living. Predation, defense, mobility, and ecological specialization all intertwine to create a complex, self-regulating system. Each creature, from the tiniest plankton to the armored trilobite, participates in the grand narrative of life, influencing evolutionary trajectories for millions of years to come. It is a world of patience, subtlety, and persistent innovation. Even environmental factors play a role in this expansion of complexity. Seasonal changes in temperature and nutrient availability influenced reproductive cycles, migration patterns, and feeding behavior. Shallow seas experienced blooms of plankton during warm periods, providing food for filter feeders and enabling rapid growth. In contrast, cooler or nutrient-poor periods may have limited growth, introducing periods of scarcity that further shaped evolutionary pressures. Life responded not just to predators, but to the rhythms of the ocean itself, attuning to its subtle cycles as we drift above the Cambrian waters. Notice how interconnected everything has become. Currents distribute food, predators shape prey. sediments are churned and oxygenated, and organisms create habitats that support other life. These oceans are alive with quiet complexity, a world that seems gentle but is defined by interaction and adaptation. Evolution unfolds not through dramatic events alone, but through the continuous, patient interplay of forces, both biological and environmental. Finally, allow yourself to imagine the calm persistence of these ancient seas. The Cambrian explosion is not chaos, it is a careful orchestration of biology, chemistry, and environment. Each organism contributes to the system, shaping and being shaped, participating in the slow, deliberate construction of complexity. As you visualize this, feel the pulse of the oceans, the rhythm of predator and prey, the subtle movements of currents and tides. The Cambrian seas were alive in a way that is still echoed in every ocean today, a reminder of the enduring patterns that govern life on Earth. As we drift gently over the Cambrian oceans, a remarkable picture emerges. These seas are alive not only with individual creatures, but with entire communities interacting, flourishing, and shaping the very nature of the marine environment. The Cambrian explosion, often described as a sudden burst of life, is better understood as a symphony of ecological innovation, a slow unfolding of interactions that produced ecosystems of remarkable sophistication. Picture the shallow continental shelves once again. Sponges anchor firmly to the seabed, filtering water and recycling nutrients. Trilobites move across the sand, leaving trails behind them, while brachiopods cling to rocks and algae carpets wave gently in the currents. Small predators weave through the sediment, searching for vulnerable prey, while burrowing worms aerate the ocean floor, promoting life even beneath the surface. Each organism, by performing its role, contributes to a larger system, a network of energy transfer, chemical cycling, and spatial organization. The complexity of these ecosystems is astounding when we consider the constraints of the Cambrian atmosphere and oceans. Oxygen levels were still moderate, yet life adapted, thriving in well-oxygenated zones while finding niches in less hospitable areas. Currents and tides distributed plankton and detritus, creating a dynamic flow of resources that supported the food web. Seasonal changes influenced reproduction, feeding, and migration, establishing cycles that organisms attuned themselves to over generations. The oceans were alive in a measured, patient way, teaching life how to survive, interact, and innovate. Predators had become more efficient, driving evolutionary innovation among prey species. The emergence of shells, spines, and specialized appendages reflects the subtle but powerful pressures of survival. But these adaptations also shaped habitats. A dense field of armored trilobites might deflect sediment in a way that protects smaller creatures beneath them. Burrowing worms might aerate sediments that nourish microbial mats. Life did not merely exist, modified its surroundings, creating feedback loops that increased both diversity and stability. Some of the most fascinating aspects of this period are the early experiments in ecological roles. Filter feeders, grazers, scavengers, and predators interacted to form protofood webs, each species filling a niche that allowed multiple organisms to coexist. Communities were structured not only by predation, but also by mutual influence. The movement of one species could enrich habitats for another, creating cascading effects that strengthened ecosystem resilience. Cambrian seas were, in essence, learning to sustain life, teaching lessons that would echo through millions of years. Beyond the shallow waters, deeper seas offered a quieter, more stable environment. Here, creatures evolved strategies for limited light and oxygen, feeding on falling organic matter and detritus. Though less visible, these deeper ecosystems were no less important. They served as reservoirs of biodiversity, spaces where experimentation in form and function could continue, away from the intense competition of shallower zones. This vertical stratification of habitats allowed life to expand into nearly every ecological niche available. maximizing the potential for evolutionary innovation. Environmental conditions also influenced this flourishing. Nutrient influxes from erosion, volcanic activity, and ocean currents created hotspots of productivity, often triggering bursts of growth and reproduction. Warm, sunlit waters supported algal blooms, feeding grazers and filter feeders in turn. Seasonal variability introduced periods of abundance and scarcity, shaping reproductive strategies and behavioral adaptations. Life was attuned to its surroundings, responding to subtle changes with a quiet persistence that would characterize the evolutionary trajectory for millions of years. The Cambrian oceans were, in this sense, both a cradle and a teacher. They nurtured the first complex communities, showing that life could organize itself, innovate, and persist even under environmental constraints. The evolutionary rules of predation, defense, and ecological specialization were being written here, slowly but surely, in the behaviors, morphologies, and interactions of the earliest animals. Every shell, every burrow, every trace fossil preserved for us today tells a story of experimentation and adaptation, a testament to life's enduring creativity as you let this vision settle. Imagine drifting above these ancient waters. Notice the patterns, the slow shuffle of trilobites across the sand, the waving of algae in currents, the gentle rise and fall of sponges filtering water. Picture small predators weaving through sediments, shaping communities through the quiet force of survival. These interactions, subtle yet profound, illustrate that complexity does not require speed or violence. Sometimes it emerges through patient, persistent engagement with the environment. Finally, consider the legacy of the Cambrian explosion. The oceans of 500 million years ago established the blueprint for marine life as we know it. The experiments in body form, behavior, and ecological organization set the stage for future innovations. More sophisticated predators, larger animals, the rise of vertebrates, and eventually life's conquest of land. The Cambrian seas were a proving ground, where the laws of life were explored and refined, quietly, patiently, and with extraordinary creativity. And as you drift in thought above this primordial world, let yourself feel the pulse of these early oceans, the rhythm of currents, the flow of nutrients, the delicate balance of predator and prey. The Cambrian explosion is more than an evolutionary event. It is a meditation on the persistence and ingenuity of life. 500 million years ago, Earth's oceans were teaching life to flourish, setting in motion the incredible story that would continue to unfold for eons. As we linger above the Cambrian continents, a closer look reveals subtle signs of life quietly persisting in hidden corners. While plants and animals have yet to colonize the land, microbial pioneers are already exploring every available niche. In moist pockets along riverbeds, shallow lakes, and temporary ponds, tiny communities of bacteria and archaea form resilient mats, some visible as thin, glistening layers clinging to rock surfaces. These microbial pioneers are the first engineers of terrestrial life, gradually transforming the chemical and physical environment around them. Imagine peering down into one of these ephemeral ponds. The surface shimmers under the sun, and within the shallow water, microbial mats filter nutrients and trap sediments. These communities secrete sticky substances that stabilize the soil, allowing finer particles to accumulate over time. In this way, microbes begin the slow work of soil formation, creating a foundation that will one day support plants. Though invisible from a distance, their influence spreads across the landscape, shaping the chemical gradients and moisture patterns essential for future colonization. The chemical composition of the early terrestrial environment is shaped as much by geology as by these microbial communities. Volcanic ash deposits deliver minerals such as phosphorus, potassium, and calcium, essential building blocks for life. Weathering of rocks releases additional nutrients into shallow soils and sediments, while streams carry these minerals to new locations, creating small pockets of enriched land. Microbes capitalize on these chemical resources, metabolizing compounds, cycling nutrients, and slowly altering the land's chemical landscape in ways that will have lasting effects, even on rocky ridges or exposed plains. Microbial life finds ways to survive. In cracks and crevices, communities cling to moisture, absorbing nutrients from mineral surfaces and maintaining a delicate balance with the environment. Cyanobacteria, capable of photosynthesis, contribute oxygen and organic compounds to these early soils. In turn, these chemical contributions subtly influence the local atmosphere and soil chemistry, laying the groundwork for the eventual emergence of more complex terrestrial life. The interplay of microbes and minerals also shapes the visual appearance of the land. Microbial mats can create faint color variations on rocks or sediment surfaces, or resinish or brownish hues that hint at their presence. Over millennia, these mats trap sediment and create microtopography, subtly changing the landscape. Small depressions hold water longer, tiny ridges collect sediment, and shallow channels form that direct moisture flow across the surface. In this way, even the smallest organisms begin the quiet sculpting of the terrestrial world. Moisture is a crucial factor in these early ecosystems. Rainfall, though intermittent, collects in low-lying areas, supporting microbial life. Evaporation and runoff distribute nutrients and water across the land, linking distant pockets of life in an invisible network. Streams and shallow ponds act as lifelines, carrying minerals, organic matter, and microbes themselves to new locations. This constant movement, though subtle, creates opportunities for colonization and expansion, gradually transforming the barren continents into more hospitable environments. Temperature fluctuations further influence microbial activity. During the day, sunlight warms shallow soils and pond surfaces, stimulating photosynthesis and metabolism. At night, cooling slows activity, conserving energy and nutrients. Seasonal variations introduce additional challenges, pushing microbes to develop resilience to drought, heat, or cold. These adaptations, though microscopic, echo across evolutionary time, providing the first lessons in survival that will be inherited by future terrestrial organisms. The Cambrian continents, though silent to the eye, are a dynamic system. Microbial mats influence erosion, sediment, deposition, and chemical cycling. Streams and rainfall shape channels and floodplains. Wind redistributes dust and minerals, while volcanic activity enriches soils with essential nutrients. Life and environment engage in a quiet dialogue, shaping each other in subtle ways that will ultimately determine the success of future terrestrial colonizers. Consider the role of oxygen and carbon dioxide in these early landscapes. Photosynthetic microbes slowly produce oxygen, though not yet enough to significantly alter the atmosphere. Carbon dioxide levels higher than modern times influence temperature, soil chemistry, and water cycles. Even without forests or large plants, these chemical dynamics regulate environmental conditions, creating microclimates and nutrient-rich patches that prime the land for future biological expansion. As we drift above these Cambrian lands, notice the gentle interplay of life and chemistry. Microbes cling to moist surfaces, rivers carry minerals, wind sculpts sediments, and volcanic ash blankets the terrain. The land appears empty at first glance, but beneath the surface, it is a quiet laboratory of adaptation, experimentation, and preparation. These hidden processes set the stage for the arrival of plants, fungi, and eventually animals, teaching life how to interact with the land and each other in ways that will echo for hundreds of millions of years. The terrestrial world of 500 million years ago is patient. It is a place where chemical landscapes, geological forces, and microbial pioneers interact slowly but deliberately, shaping a foundation for life yet to come. Even in silence and apparent emptiness, the land is alive, responding to every rainfall, every mineral deposit, every microbial mat. And as you imagine this quiet world, feel the rhythm of these subtle processes, the slow pulse of life preparing to flourish on land for the first time. As we rise above the Cambrian landmasses, a stark contrast to the bustling oceans becomes immediately apparent. The continents of this era are vast, largely barren, and uninhabited by plants or animals. Imagine them stretching endlessly under a pale sun, their rocky surfaces marked by subtle geological textures, ridges, valleys, and occasional shallow lakes. Unlike the vibrant, life-filled seas, these terrestrial landscapes appear silent, patient, and waiting. The soil, if it can be called that, is thin and young. Weathering from wind and occasional rain creates sediments, but there are no roots to bind the ground or microbial mats to enrich it. The land is shaped primarily by tectonic forces, volcanic activity, and erosion. Mountains rise slowly, rivers carve shallow channels, and occasional floodplains form where rainfall accumulates. Streams trickle into the shallow margins of seas, carrying minerals and nutrients from the continents into the water, sustaining marine life while leaving the land itself quiet and barren. Without vegetation, sunlight bathes the land unobstructed. Shadows are cast solely by the contours of rocks, cliffs, and hills. The sun's warmth interacts directly with the surface, heating rock and sediment during the day, releasing that warmth at night. Temperature fluctuations are more pronounced than in the oceans. Days can be warm, nights cooler, and seasonal changes introduce subtle variations across latitudes. Yet even in these seemingly harsh conditions, chemical and physical processes quietly sculpt the land, laying the foundation for life's eventual colonization. The air over these barren continents carries a faint, mineral-rich scent. Volcanic gases, weathered rock particles, and occasional sea spray drift inland, mingling in the atmosphere. Winds sweep freely across plains and valleys, shaping dunes and distributing sediments. Dust storms occasionally rise, lifting fine particles into the sky and transporting them across vast distances. In this silent world, even these small movements of air and dust play a crucial role, influencing the chemical composition of soils and the distribution of minerals that will, in the future, support life, while life has not yet taken hold on land. Microbial communities may persist in hidden niches. Moist areas near lakes, tidal flats, or temporary ponds could host primitive bacteria or microbial mats, forming a subtle, invisible network of life. These microorganisms participate in nutrient cycling, subtly altering the chemical composition of the substrate and preparing it for more complex life in the distant future. The land may seem empty, but it is quietly alive at a microscopic level, foundation upon which life will eventually flourish. Geological activity also plays a defining role in shaping terrestrial landscapes. Volcanic eruptions punctuate the calm, releasing lava and gases that reshape terrain and contribute to soil formation. Erosion by wind and water slowly carves canyons, channels, and valleys, creating habitats that will later be colonized by plants and animals. Even the barren continents are dynamic, constantly transformed by physical forces. And these changes create the conditions necessary for the eventual emergence of life on land. Consider the contrast with the oceans we observed previously. The seas teem with activity, a symphony of evolution and interaction, while the continents are quiet, empty stages. Yet this emptiness is not absence, it is potential. The land masses store energy in the form of minerals, retain heat from the sun, and respond to weather and geological activity. They are waiting patiently, a blank canvas for life's first experiments in terrestrial colonization, where adaptations to dryness, sunlight, and gravity will eventually be required, even in the absence of plants and animals. The Cambrian land is not devoid of subtle processes. Water erosion creates intricate patterns along riverbeds and floodplains. Rocks crack under the influence of temperature shifts, forming small fissures and crevices that may harbor future habitats. Mineral deposits from volcanic ash or weathered rock create chemical gradients, shaping the early chemical environment of soils. These invisible, slow processes are critical. They establish the physical and chemical scaffolding upon which terrestrial life will later thrive. The absence of life, also, means that the land's visual and auditory environment is calm and unbroken. No rustle of leaves, no animal calls, only the whisper of wind, the occasional patter of rain, and the subtle shifts of the Earth's surface. This serenity, though seemingly empty, provides a unique perspective on the early Earth. It reminds us that life is not simply the sum of creatures present, but also the interplay of environmental conditions, chemical processes, and physical forces that create possibilities as you let this vision settle. Picture drifting over these silent continents. Observe the rocky ridges, the shallow streams, and the subtle textures of weathered soil. Feel the calm of a world largely untouched by biology, yet quietly dynamic. Understand that this emptiness is fertile not in the sense of lush vegetation, but as a space of potential. The continents of the Cambrian are patiently preparing for life, shaped by wind, water, and geological forces, waiting for the day when plants will take root and animals will venture from the seas onto land. The silent terrestrial world reminds us that Earth's story is a slow unfolding. Oceans may see rapid diversification, but the land has its own patience, measured in millions of years. Every grain of sediment, every trickling stream, every chemical reaction in the soil contributes to a readiness that will eventually allow life to flourish. And as you imagine drifting above these early continents, feel the quiet anticipation, the latent energy, and the invisible processes quietly shaping the stage for life's next great chapter. As we continue our flight above the Cambrian continents, it becomes clear that these silent lands are anything but inactive, though plants and land animals have yet to emerge. The stage is being meticulously set for life to eventually thrive beyond the oceans. Every geological process, every microbial colony, and every mineral deposit contributes to a subtle, patient preparation for the green invasion that will one day transform the planet. Picture shallow lakes and small ponds scattered across the landscape. Microbial mats coat the sediment, slowly cycling nutrients and oxygen. Cyanobacteria and other photosynthetic organisms secrete compounds that stabilize soil, allowing sediments to accumulate and creating microenvironments capable of supporting more complex life. These tiny communities are the architects of the land's fertility, laying the groundwork for the first plants that will eventually colonize the continents. The chemical interactions of the pre-plant era are crucial. Volcanic eruptions deliver ash and minerals, while erosion transports sediments and nutrients from mountains to lowlands and river valleys. Rainwater dissolves these minerals, creating fertile pockets across the terrain. Microbial activity enhances nutrient availability by breaking down compounds and releasing essential elements like phosphorus, potassium, and trace metals. Slowly, over millions of years, the land becomes chemically ready to host autotrophic organisms with more complex structures, plants that can anchor in soil, capture sunlight efficiently, and initiate photosynthesis at a larger scale. Temperature and moisture patterns also shape readiness for life. Seasonal rains fill temporary ponds, creating moist refuges for microbial communities. Evaporation and runoff distribute these nutrients to surrounding areas, enriching soils in shallow depressions. Rocks and sediments store thermal energy from sunlight, moderating microclimates and providing stability in temperature extremes. Even in the absence of visible life, these environmental rhythms nurture conditions favorable for colonization, creating patches of habitability across an otherwise barren landscape. Geological forces continue their quiet work. Tectonic movements create mountains and valleys, while wind and water sculpt the surfaces of continents. Cracks, fissures, and shallow depressions form naturally, offering the first microhabitats where life can take hold. Volcanic soils rich in minerals create islands of fertility. Erosion distributes these nutrients, subtly linking distant regions into networks of chemical and physical resources. Each of these processes, invisible on a day-to-day basis, contributes to the long-term habitability of land, the absence of animals. On land allows microbes and chemical processes to act unhindered. Burrowing and grazing behaviors, which later shape soil structure, are still absent. But microbial activity compensates by stabilizing sediments and cycling nutrients. The land is quietly engineered by these invisible forces, demonstrating that life does not always require complexity to influence its environment. Even simple organisms can shape the future in profound ways. Atmospheric conditions also play a role in preparing the land for future colonization. Though oxygen levels remain low compared to modern times, localized increases around photosynthetic microbial mats enrich the air near the surface. Carbon dioxide, abundant in the atmosphere, contributes to a warmer climate, ensuring that seasonal temperature swings are not extreme enough to prevent colonization. These subtle chemical and atmospheric dynamics are the invisible scaffolding for the green revolution that will follow in the coming hundreds of millions of years. Even the visual and auditory experience of these early continents has significance. The quiet, open expanses allow sunlight to reach every corner of the land, creating ideal conditions for eventual photosynthetic life. The rhythmic patterns of wind and water subtly sculpt the terrain, forming gentle undulations and small depressions that will one day host plants and early land-dwelling animals. While the human eye may perceive emptiness, the land is alive with potential, shaped by a slow, deliberate interplay of physical, chemical, and microbial processes. One of the most remarkable aspects of this era is the patience of the Earth itself. Oceans may host rapid bursts of evolution, but the continents move at a geological pace. Sediments accumulate slowly, nutrients disperse gradually, and microbial communities expand incrementally. Yet this patience is effective, ensuring that when life eventually arrives on land, encounters a landscape ready to support its growth. The stage has been set with invisible precision: fertile soils, chemical gradients, protective microhabitats, and consistent environmental rhythms. As you drift across these silent continents, imagine the eventual emergence of plants taking root. Each step of this preparation, the accumulation of nutrients, the stabilization of sediments, the subtle shaping of microclimates represents a prelude to life's grand expansion from water to land. The pre-plant era demonstrates that life's progress is not only biological, but environmental. Evolution is guided as much by the readiness of the planet as by the organisms themselves. Finally, as your imagination lingers above the Cambrian land, feel the calm anticipation of a world on the brink of transformation. Microbial pioneers persist in quiet corners. Chemical processes unfold over millennia, and geological forces continue their patient sculpting. The land is waiting, not empty, but full of invisible activity, quietly preparing for a future dominated by green. And when that day arrives, plants will seize the opportunity, establishing the first terrestrial ecosystems and setting in motion the next chapter of Earth's extraordinary story. As we shift our focus from land and oceans to the invisible yet essential workings of Earth's chemistry, a new dimension of life comes into view: the biogeochemical cycles that govern the movement of key elements through the planet. Even 500 million years ago, these cycles were quietly orchestrating the conditions for life, regulating energy, nutrients, and atmospheric balance. Though largely invisible, they form the pulse of the planet, a rhythm upon which all life depends. Let's begin with carbon, the backbone of life itself. In the Cambrian oceans, organic molecules are constantly created and recycled. Phytoplankton and microbial mats capture carbon dioxide from the water and atmosphere, transforming it into the building blocks of cells. When creatures die, their bodies sink to the seafloor, becoming sedimentary deposits that lock away carbon for millennia. This slow sequestration balances the carbon cycle, regulating atmospheric levels and influencing the climate. Even subtle shifts in this cycle can ripple across the ecosystem, affecting temperature, nutrient availability, and evolutionary pressures. Meanwhile, oxygen, though less abundant than in modern times, circulates quietly between oceans and atmosphere. Photosynthetic microbes release oxygen as a byproduct, slowly enriching localized environments. Oxygen diffuses through the water and, over time, increases concentrations in shallow seas. These oxygen-rich zones become oases for aerobic life, enabling higher metabolic rates and more complex body structures. At the same time, oxygen participates in chemical weathering on land, reacting with minerals to slowly shape soils and release nutrients, linking the atmosphere, oceans, and continents in an invisible web of life-supporting processes. Nitrogen, often overlooked yet essential, completes this triad of life-sustaining elements. Nitrogen-fixing microbes convert atmospheric nitrogen into forms usable by living organisms, supporting growth in both oceans and nascent terrestrial niches. This cycle maintains the availability of an element critical for proteins, nucleic acids, and enzymes. Even without large plants or animals on land, nitrogen is cycling through microbial communities, seawater, and sediments, silently preparing the chemical groundwork for future life. The interplay between these three cycles, carbon, oxygen, and nitrogen, forms the fundamental rhythm of Earth's early ecosystems. Carbon provides structure, oxygen enables energy production, and nitrogen fuels growth. Each cycle interacts with the others, creating feedback loops that regulate climate, nutrient availability, and the pace of biological activity. In the Cambrian seas, these cycles are particularly dynamic, as the explosion of life produces immense quantities of organic matter that feeds back into the chemical system, reinforcing the delicate balance between biology and chemistry. Consider how carbon moves through the oceans. Phytoplankton absorbs CO during photosynthesis, creating organic compounds that sustain the food web. Predators, grazers, and scavengers consume this biomass, releasing carbon back into the water through respiration. When organisms die, decomposition or burial in sediments captures carbon in long-term storage. The sedimentary record, preserved for hundreds of millions of years, tells the story of these processes, tracing the rise and fall of species, the expansion of ecosystems, and the shifting balance of the Cambrian carbon cycle. Oxygen, in turn, responds to this movement of carbon. As more organic matter is produced and buried, oxygen levels in local waters can increase, enabling more complex life to thrive. Conversely, decomposition consumes oxygen, creating hypoxic zones that challenge survival. These local variations in oxygen concentration drive adaptations in mobility, respiration, and body structure, shaping evolutionary pathways. The chemical environment is never static. It is a living system, responsive and interactive as the organisms that inhabit. Its nitrogen cycle also interacts with carbon and oxygen in subtle ways. Nitrogen fixation enables growth, supporting larger populations and more complex food webs. Denitrification, the process of returning nitrogen to the atmosphere, is balanced by microbial activity and environmental conditions. Together, these processes maintain a stable supply of essential nutrients, ensuring that life in the oceans can flourish even amid changing conditions. The interplay of carbon, oxygen, and nitrogen is a quiet, invisible symphony, orchestrating life's potential at scales both microscopic and planetary. Even the smallest fluctuations in these cycles can have profound effects. Variations in carbon dioxide influence climate, affecting ocean currents, temperature gradients, and the distribution of life. Oxygen availability governs metabolic capacity and the potential for complex multicellular organisms. Nitrogen controls productivity, dictating which areas of the ocean can support dense populations. Over millions of years, these subtle chemical rhythms shape the trajectory of evolution, preparing the stage for new forms of life and increasingly intricate ecosystems as we drift above the Cambrian landscape and oceans. Visualize this invisible network of chemical flows. Carbon is absorbed, transformed, and stored. Oxygen ebbs and flows, enabling life to breathe and flourish. Nitrogen cycles silently, sustaining growth and complexity. Though unseen, these processes are as vital as the movement of tides or the rise of continents. They are the lifeblood of the planet itself. Even today, we can observe the legacy of these early cycles in the sediments, isotopic records, and fossilized organisms preserved across continents. They reveal the deep interconnections between life and chemistry, demonstrating that evolution is not only a biological process, but also a chemical and planetary one. The Cambrian world teaches us that Earth's living systems are inseparable from its biogeochemical foundations, that every organism, from the tiniest microbe to the largest predator, participates in this vast, invisible network. Finally, allow yourself to feel the rhythm of these cycles as you drift above the Cambrian seas and continents. The movement of carbon, oxygen, and nitrogen is slow, patient, and unbroken. It is a pulse that has sustained life for eons, creating conditions for the growth, adaptation, and flourishing of every organism that will follow. Even as you listen, your mind can trace these quiet flows, feeling the deep interconnectedness of life and Earth, and appreciating the invisible processes that have shaped our planet for 500 million years. As we hover above the Cambrian oceans, it becomes apparent that life and chemistry are engaged in a complex, interwoven dance. The cycles of carbon, oxygen, and nitrogen are not isolated. They respond to one another, creating feedback loops that regulate productivity, sustain ecosystems, and shape evolutionary pressures. Understanding these interactions allows us to glimpse the invisible dynamics that enabled the Cambrian explosion to unfold with such vibrancy. Consider carbon first. As phytoplankton and microbial mats fix carbon through photosynthesis, they produce the energy and organic matter that fuel higher trophic levels. Grazers consume these primary producers, predators consume the grazers, and detritivores recycle the remains back into the system. Every transfer of carbon involves energy, nutrients, and oxygen. Increased burial of carbon in sediments subtly increases oxygen levels in surrounding waters, which in turn supports the metabolism of more active and complex organisms. The cycles are intertwined, and one change in carbon flow can ripple through oxygen levels, nutrient availability, and biological activity. Oxygen itself is a dynamic participant in this system. As photosynthetic organisms generate oxygen, local concentrations rise, creating pockets of rich metabolic potential. These oxygenated zones allow the evolution of larger, more mobile, and metabolically demanding species. Conversely, areas where decomposition consumes oxygen become temporary loxygen zones, forcing organisms to adapt, migrate, or develop specialized strategies for survival. Oxygen levels thus fluctuate, not just globally, but locally, shaping the distribution, behavior, and evolution of marine communities. Nitrogen plays an equally subtle but critical role. Nitrogen-fixing microbes provide essential nutrients that allow populations to grow, supporting complex food webs. Denitrifying processes, meanwhile, return nitrogen to the atmosphere, preventing its overaccumulation. The balance of nitrogen, carbon, and oxygen creates a delicate system. If nitrogen is abundant, productivity can spike, drawing down carbon and producing oxygen. If nitrogen becomes limited, primary productivity declines, influencing predator-prey dynamics and altering the pace of ecological interactions. In this way, the three cycles are locked in an ongoing feedback loop that sustains both chemical balance and biological diversity. The interactions of these cycles influence spatial patterns in the oceans. Upwelling zones where deep, nutrient-rich waters rise to the surface become hotspots of productivity, fueling blooms of plankton and feeding entire ecosystems. Oxygen levels in these regions can rise rapidly due to photosynthetic activity, while carbon is temporarily sequestered in living biomass. When organisms die and sink, carbon returns to the depths, creating long-term storage in sediments. Nitrogen cycling ensures that these nutrient-rich zones continue to support life, maintaining the intricate dance of growth, consumption, and decomposition. Even small-scale processes matter. Sediment layers, microbial mats, and burrowing activity alter local chemical conditions, producing microenvironments that influence species distribution and diversity. Shifts in water temperature, current patterns, and light penetration modulate photosynthesis and respiration, indirectly affecting carbon, oxygen, and nitrogen fluxes. The interplay of physical, chemical, and biological factors creates a self-regulating system, where feedback loops maintain stability while enabling incremental innovation. These interactions are not merely mechanical, they shape evolution itself. Predators respond to oxygen-rich zones by evolving more active hunting strategies. Prey species adapt to variable nutrient availability by developing faster growth rates or more efficient feeding structures. Microbial communities adjust to chemical fluctuations, altering nitrogen fixation or carbon sequestration rates. The cycles themselves become agents of selection, guiding the evolution of life at a planetary scale. Visualize this system as a vast, invisible web connecting every organism and every chemical process. Each breath of oxygen, each molecule of carbon dioxide absorbed, and each nitrogen atom fixed contributes to a global network of energy and nutrients. Cambrian oceans are not only teeming with visible life, they are alive chemically, with feedback loops, reservoirs, and exchanges that regulate the entire ecosystem. Life and chemistry are inseparable, co-evolving in a way that ensures stability, resilience, and the potential for ever greater complexity. Environmental shifts further illustrate the cycle's subtle power. Seasonal fluctuations in temperature, light, and nutrient input affect primary production, which in turn modifies carbon and oxygen levels. Localized blooms of plankton temporarily alter the chemistry of shallow waters, increasing oxygen and drawing down CO. Conversely, areas of decomposition and sedimentation can deplete oxygen, creating microhypoxic conditions that challenge organisms. In this way, even the tiniest environmental change can cascade through the system, demonstrating the sensitivity and responsiveness of Earth's biogeochemical cycles. The Cambrian biogeochemical networks are slow and patient, operating over days, seasons, and millennia. Yet their influence is profound. They determine where life thrives, how ecosystems evolve, and which innovations succeed. From the smallest microbial mat to the most agile trilobite, every organism participates in these cycles, shaping and being shaped by the invisible currents of carbon, oxygen, and nitrogen. Life is not merely surviving, it is co-creating the very environment in which it exists. As you drift above these ancient oceans, picture the silent rhythm of the cycles: carbon flowing through organisms and sediments, oxygen rising and falling in delicate balance, nitrogen circulating to sustain growth. Imagine these processes continuing day after day, season after season, quietly shaping evolutionary opportunities, supporting diversity, and sustaining life. These cycles are the pulse of the Cambrian world, invisible yet indispensable, a constant reminder that life and planet are inseparable. As we continue drifting above the Cambrian oceans and continents, it becomes evident that the biogeochemical cycles of carbon, oxygen, and nitrogen are more than mere chemical processes. They are the invisible architects of life itself. Every fluctuation, every exchange, every cycle has consequences that echo across eons, shaping ecosystems, guiding evolution, and determining which forms of life will thrive or fade away. The legacy of these cycles is profound. Carbon, continuously captured by photosynthetic organisms and buried in sediments, stabilizes the atmosphere and regulates climate. These processes maintain a delicate balance that prevents extreme temperature swings while providing the building blocks for life. Each molecule of carbon that flows through organisms contributes to growth, energy storage, and reproduction, connecting every creature to a global network that extends from the tiniest microbe to the largest Cambrian predator. Oxygen, slowly accumulating due to microbial photosynthesis, enables new possibilities for life. Even slight increases in oxygen concentration allow more energy-intensive metabolisms, supporting larger body sizes and complex behaviors. Cambrian ecosystems begin to flourish because oxygen availability permits higher activity levels and evolutionary experimentation. Local oxygen-rich zones become cradles of innovation where adaptations emerge, driving diversification and complexity. This invisible element, circulating quietly through water and atmosphere, is both a lifeline and a selective force shaping the evolutionary destiny of organisms. Nitrogen, often underestimated, sustains growth and productivity. The cycle of nitrogen fixation and denitrification ensures that nutrients remain available for life to flourish. Without nitrogen, primary production would stagnate, slowing the flow of energy through food webs. Nitrogen's steady circulation forms the foundation of growth, enabling populations to expand, species to diversify, and ecosystems to become more intricate. In this sense, nitrogen is both a resource and a regulator, silently orchestrating life's potential. The interactions among these three cycles create feedback loops that maintain stability and resilience. High carbon burial leads to increased oxygen, which allows more complex organisms to thrive, producing more biomass, which in turn influences carbon storage. Nitrogen availability regulates productivity, ensuring that ecosystems do not collapse under nutrient stress. These interwoven processes form a self-regulating planetary system, a delicate balance where chemistry and biology continuously influence one another over millions of years. These cycles leave tangible traces in the fossil and sedimentary record. Carbon-rich deposits indicate periods of high biological productivity. Oxygen isotopes reflect atmospheric and oceanic changes, and nitrogen signatures reveal patterns of nutrient availability. Even today, scientists can read these records to understand how life and chemistry coeved during the Cambrian, revealing the invisible scaffolding that supported one of Earth's most dynamic periods of biological innovation. The cycles also demonstrate the universality of life's dependence on chemical flows. From shallow microbial mats to open ocean plankton blooms, every organism participates in these networks. They consume, release, and transform carbon, oxygen, and nitrogen in ways that ripple across the ecosystem. Evolution is guided not only by predation or environmental pressure, but also by the availability and movement of these essential elements. Life is both sculptor and sculpted, shaping its environment while being shaped by it. Even on land, these cycles play a subtle role. Nutrients transported by rivers from continents into shallow seas provide the building blocks for marine productivity. Oxygen levels in nearshore waters influence coastal microbial activity. Nitrogen carried from weathered rocks enriches oceanic ecosystems. Although land is largely barren in the Cambrian, it participates indirectly, linking terrestrial and marine chemistry in a global cycle that sustains life. The planet functions as a unified system, each component connected to the next, even when life seems absent in certain regions. As you imagine drifting over these early oceans, envision the slow, patient flow of elements, carbon absorbed and released, oxygen diffusing and accumulating, nitrogen cycling and replenishing. These movements are invisible, yet essential, creating conditions for thriving ecosystems, shaping evolutionary pressures, and preparing the way for future complexity. They are the heartbeat of Earth, persistent and steady. Maintaining balance across time and space, the Cambrian world teaches a profound lesson. Life cannot be separated from its chemical and physical environment. The flourishing of species, the diversification of body plans, and the evolutionary innovations of this period are all made possible by the invisible cycles of carbon, oxygen, and nitrogen. These cycles are more than background processes. They are active participants in the story of life, guiding its potential and determining the trajectory of evolution. Finally, as your imagination floats above the Cambrian seas, let yourself feel the rhythm of these cycles. Visualize the movement of elements through water, sediment, and atmosphere. Sense the invisible web that connects every organism, every chemical reaction, and every environmental change. Appreciate the patient orchestration of the planet, a system in which life and chemistry coeve, supporting and regulating one another. The legacy of these cycles is profound, not only for the Cambrian world, but for every stage of Earth's history, laying the foundation for the future expansion of life and the complex, interconnected ecosystems that will eventually dominate the planet. As we continue our journey through the Cambrian world, we must pause to consider the hidden stresses that shaped life's evolution. While oceans teemed with burgeoning diversity, and microbial and planktonic communities thrived, Earth itself was a dynamic and sometimes unforgiving system. Geochemical events, subtle shifts in chemistry, fluctuations in nutrients, and localized crises served as both warnings and opportunities, shaping ecosystems in ways that are still written in the rock record today. Imagine a vast, shallow sea, stretching endlessly under the pale sunlight. Beneath the surface, oxygen levels vary, nutrients rise and fall, and the composition of seawater subtly changes. These variations might appear insignificant, but for early marine life, even small chemical shifts could determine survival or extinction. An influx of minerals from volcanic activity, a sudden depletion of oxygen in a bay, or a change in nitrogen availability could tip the delicate balance of an ecosystem, creating localized stress zones that challenge the adaptability of species. One type of geochemical stress arises from fluctuations in oxygen concentration. Shallow waters might experience brief hypoxic episodes, where oxygen levels drop low enough to strain or kill sensitive organisms. Mobile creatures could escape to better oxygenated waters, but sessile organisms, or those with limited mobility, would face the risk of mortality. Over geological time, these repeated stress episodes drive evolution, favoring traits such as enhanced mobility, improved respiratory efficiency, or tolerance to oxygen conditions. Life, in essence, learns to cope with challenge through adaptation. Nutrient availability, particularly of carbon, nitrogen, and phosphorus, also plays a crucial role. Variations in riverine input, weathering of rocks, or upwelling events can create sudden spikes or shortages in essential elements, while abundant nutrients can trigger blooms of primary producers. Supporting rapid population growth, scarcity imposes limits. These cycles of abundance and scarcity produce natural selection pressures that influence growth rates, reproductive strategies, and feeding behaviors. Even within a single shallow bay, these chemical oscillations create pockets of ecological opportunity and challenge, shaping both community structure and species diversity. Volcanic activity introduces another layer of geochemical stress. The Cambrian continents, still tectonically active, periodically release ash and mineral-laden waters into the oceans. These inputs can enrich local environments, stimulating microbial growth, or, conversely, introduce toxic elements that depress biological activity. The timing, scale, and location of these events determine their impact. For some species, volcanic enrichment is a boon. For others, an abrupt crisis. Over time, these episodic events act as selective filters, sculpting ecosystems and encouraging resilience. Temperature fluctuations also impose subtle stress. The Cambrian world was warmer than today, but localized variations in water temperature influenced metabolism, growth, and reproduction. Organisms adapted to stable thermal conditions may experience stress when currents shift or seasonal variations intensify. Microbial mats, plankton, and early predators all respond to these changes, adjusting their activity, distribution, or behavior. These environmental pressures, while invisible to a casual observer, leave enduring marks in evolutionary history. Another form of geochemical stress comes from the accumulation of organic matter in sediments. In areas with high productivity, decaying material consumes oxygen, creating hypoxic or anoxic zones near the seabed. These chemical dead zones prevent many organisms from inhabiting certain areas. Yet they also create niches for specialized life forms capable of surviving in low-oxygen conditions. Over millions of years, such zones drive adaptation and diversification, encouraging evolutionary experimentation in both metabolism and behavior. Consider also the subtle effects of ocean acidity, influenced by carbon dioxide levels in the atmosphere and water. Shifts in pH affect the solubility of minerals, the growth of calcareous organisms, and the stability of chemical compounds in the water. Even minor changes in acidity can impact the formation of shells, the availability of nutrients, and the overall health of marine communities. Early marine life is constantly negotiating these invisible chemical pressures, balancing survival with the opportunities presented by their dynamic environment. These geochemical stress events, while seemingly minor on a human timescale, operate across millennia to shape the trajectory of evolution. Life is never static in the Cambrian oceans. It responds to chemical signals, adapts to local crises, and migrates to exploit favorable conditions. Each stress episode, whether hypoxia, nutrient fluctuation, or chemical enrichment, provides both a challenge and a lesson, honing resilience, adaptability, and innovation in emerging ecosystems. Finally, as you imagine drifting above these Cambrian seas, sense the invisible forces at play. The water is alive not only with visible creatures, but with chemical currents, nutrient pulses, and oxygen gradients. Microbes, plankton, and early predators navigate these challenges instinctively, their behaviors shaped by the pressures of their environment. Even in a world dominated by chemical subtleties, evolution marches forward, guided by the quiet, relentless influence of geochemical stress. As we float above the Cambrian oceans, it becomes clear that geochemical stress events do more than challenge individual organisms. They ripple outward, influencing entire ecosystems. A local drop in oxygen, a nutrient imbalance, or a shift in pH may appear minor in isolation, but these events cascade through food webs, affecting predators, prey, and microbial communities alike. Life responds collectively, and in doing so, evolves in fascinating and sometimes unexpected ways. Consider a shallow bay experiencing a brief oxygen depletion. Sessile organisms, unable to move, may perish or enter dormancy. Mobile predators must search for better oxygenated waters, while opportunistic scavengers exploit the sudden availability of resources from dying organisms. These localized crises drive competition and innovation, favoring traits like enhanced mobility, improved sensory perception, or behavioral flexibility. Over generations, these selective pressures mold populations, encouraging the emergence of new strategies for survival. Nutrient fluctuations have similarly profound consequences. A sudden influx of phosphorus or nitrogen, perhaps from upstream erosion or upwelling, can trigger bursts of primary productivity. Phytoplankton blooms provide a feast for grazers, which in turn support predators. Conversely, nutrient depletion can create scarcity, slowing growth and forcing species to compete more aggressively. These oscillations in resource availability establish natural checks and balances, regulating population sizes and promoting ecosystem resilience. Life is constantly negotiating this invisible chemical landscape, adapting not only to immediate challenges, but also to recurring patterns over time. Volcanic activity adds yet another layer of complexity. When ash, minerals, or dissolved gases enter the ocean, they alter local chemistry dramatically. Some species flourish in enriched waters, growing faster or reproducing more successfully, while others struggle with toxicity or environmental instability. These pulses of change act as evolutionary catalysts, encouraging diversification and experimentation in feeding strategies, body structures, and reproductive modes. Geochemical crises, though disruptive, are often the crucibles in which innovation occurs. Temperature shifts, both seasonal and episodic, influence the metabolism of Cambrian organisms. Warmer waters increase metabolic rates, allowing faster growth and more active predation, while cooler zones slow activity, creating refuge areas or forcing migration. The interplay between thermal conditions and chemical stresses further shapes evolutionary outcomes. For example, a hypoxic zone in warm waters may select for more efficient respiratory systems, while cooler, nutrient-rich areas favor slower, energy-efficient growth strategies. These patterns, repeated across millennia, guide the development of new life forms. Chemical dead zones. Regions of oxygen depletion on the seafloor are particularly influential. While inhospitable to many species, they provide niches for specialized organisms, including anaerobic microbes and scavengers adapted to oxygen conditions. These zones drive the evolution of metabolic diversity, encouraging alternative strategies for energy production and survival. Over time, species capable of exploiting these challenging environments gain advantages in resource competition, setting the stage for further innovation and complexity in marine ecosystems. Even ocean acidity, subtly modulated by carbon dioxide levels, leaves a lasting imprint. Slightly lower pH affects shell formation in early calcareous organisms, influencing which species can survive and thrive. Populations that adapt to variable acidity gain resilience, while others decline. These pressures, though invisible to the naked eye, drive morphological changes and species differentiation, demonstrating the profound influence of chemistry on evolutionary pathways. The cascading effects of geochemical stress are also evident in predator-prey dynamics. Hypoxia or nutrient fluctuations may temporarily reduce prey abundance, challenging predators to adapt hunting strategies or diversify their diets. Over time, these pressures shape anatomy, behavior, and sensory adaptations. Species capable of navigating these shifting conditions survive and proliferate, while others vanish from the record. In this way, geochemical stresses become indirect architects of evolutionary complexity, guiding the trajectory of life toward ever more intricate forms at a broader scale. These events link ecosystems across regions. Oxygen-depleted zones, nutrient pulses, and volcanic inputs are rarely confined to single bays or shallow seas. Currents distribute chemical signals, sediments, and nutrients, connecting distant communities. A stress event in one area may ripple outward, influencing population dynamics, migration patterns, and evolutionary pressures elsewhere. The Cambrian oceans operate as a connected system, where local chemical disturbances have global implications for life. As we drift above this ancient world, visualize the invisible network of cause and effect. Chemical fluctuations, oxygen levels, nutrient availability, and temperature variations all interact, creating dynamic pressures that shape the behavior, physiology, and evolution of marine organisms. Every stress event is a teacher guiding adaptation, survival, and diversification. Even in the apparent chaos of environmental change, life finds ways to innovate, thrive, and persist. Finally, Sense the rhythm of the Cambrian seas, a quiet pulse of challenge and response, where geochemical stress events shape evolution and ecosystems. These invisible pressures, operating over millennia, prepare the stage for the explosion of complexity and diversity that defines the Cambrian era. Life is resilient, adaptable, and responsive, co-evolving with the chemistry of the planet, demonstrating that survival is not only about strength or size, but about the capacity to respond to the subtle/late, unrelenting rhythms of Earth's geochemical heart. As we continue our serene journey over the Cambrian oceans, it becomes evident that geochemical stress events are more than fleeting disturbances. They leave lasting legacies, guiding evolutionary pathways and shaping the composition of ecosystems for millions of years. While some crises may appear sudden or localized, their long-term impact resonates across oceans and sediments, creating selective pressures that define the future of life. Consider oxygen fluctuations, which occur in shallow seas and estuaries. Short-term hypoxia challenges organisms to adapt, migrate, or perish. But over time, repeated exposure favors species with efficient respiratory systems, behavioral flexibility, and enhanced mobility. These adaptations, honed by chemical stress, become permanent features of populations. Oxygen, in its subtle ebb and flow, sculpts anatomy, physiology, and behavior, leaving an evolutionary signature that persists long after the immediate crisis has passed. Nutrient imbalances, spikes, or shortages of carbon, nitrogen, and phosphorus also shape the evolutionary landscape. Periods of abundance promote rapid growth and reproduction, leading to population booms and increased competition. Conversely, scarcity encourages efficiency, specialization, and opportunistic strategies. Over generations, these nutrient-driven pressures refine species' ecological roles, diversify food webs, and foster complex interactions between predators, prey, and primary producers. The cyclic nature of nutrient stress ensures that ecosystems remain dynamic, constantly adapting to the invisible chemical rhythms of the planet. Volcanic activity introduces episodic chemical perturbations that leave an indelible mark. When minerals, ash, and gases enter oceans, they create both opportunities and challenges. Some species capitalize on enriched conditions, growing faster or reproducing more effectively, while others struggle with toxicity or habitat alteration. Over long timescales, these episodic events act as evolutionary filters, promoting resilience, innovation, and adaptability. In essence, volcanoes are catalysts of change, shaping marine communities and indirectly guiding evolutionary trajectories. Temperature variability, subtle yet persistent, also leaves enduring effects. Warm waters accelerate metabolic rates, encouraging more active predation and faster growth. Cooler waters, in contrast, promote energy conservation and slower life cycles. Organisms exposed to fluctuating thermal environments develop physiological flexibility, behavioral adaptations, and ecological versatility. These traits, born of repeated stress, become part of the evolutionary toolkit that allows life to survive and thrive in an ever-changing world. Chemical dead zones on the seafloor, regions of low oxygen caused by the accumulation of organic matter, drive the evolution of specialized life forms. Microbes capable of anaerobic metabolism thrive where most other organisms cannot. Detritivores and scavengers adapt to exploit limited resources. Over time, these adaptations propagate, influencing the diversity and ecological roles of future species. Dead zones, while inhospitable, act as incubators of evolutionary experimentation, revealing that crises often create the conditions for innovation. Even ocean acidity, influenced by carbon dioxide fluctuations, shapes the long-term fate of life. Variations in pH affect mineral solubility, shell formation, and enzymatic processes. Organisms that tolerate subtle changes in acidity gain competitive advantages, while sensitive species may decline or vanish. This invisible selective force fosters resilience, drives morphological and physiological innovation, and ensures that marine ecosystems remain dynamic and adaptable. The combined effects of oxygen variation, nutrient shifts, volcanic pulses, temperature changes, and chemical stressors create cascading consequences for the entire marine food web. Predators adapt to prey availability, prey modify feeding strategies, and microbial communities adjust nutrient processing. These feedback loops, repeated over millennia, produce evolutionary innovations that define the structure, function, and diversity of Cambrian ecosystems. Life does not merely endure crises, it evolves through them, transforming challenges into opportunities for adaptation and growth. GEOCHEMICAL stress events also leave lasting records in sediments, isotopic signatures, and fossil distributions. Scientists studying the Cambrian era can trace the influence of these chemical fluctuations, reading the story of environmental challenges and biological responses. Carbon isotopes reveal episodes of enhanced burial or productivity. Oxygen proxies indicate hypoxic events. Nitrogen markers show the cycling of nutrients through ecosystems. These records testify to the enduring influence of chemical stresses on evolution, demonstrating that life and planet are inseparable, co-evolving systems. Finally, imagine drifting above the Cambrian oceans, sensing the invisible but relentless influence of geochemical crises. These subtle forces, acting over centuries and millennia, guide adaptation, promote resilience, and foster complexity. Life is sculpted not only by predation or competition, but by the chemistry of its environment, the rhythm of elemental cycles, and the challenges imposed by a dynamic planet. Each stress event, no matter how small or localized, contributes to the evolutionary story, leaving an enduring legacy in the diversity, adaptability, and resilience of life. As you let these thoughts settle, recognize the quiet, persistent power of geochemical stress. Even in a world dominated by invisible chemical shifts, life flourishes, innovates, and perseveres. The Cambrian oceans, shaped by countless crises, are a testament to the interplay between chemistry and biology, a subtle, enduring dance that has prepared Earth for millions of years of evolutionary experimentation and success. The planet is alive, responsive, and patient, nurturing life even through the quiet pressures of chemical change. As we lift gently above the Cambrian world, leaving the oceans behind and ascending toward the sky, a new perspective emerges, a view of Earth not as a collection of individual habitats, but as a whole, dynamic planet. From this vantage point, the interplay of atmosphere, oceans, and landforms becomes a living tapestry, ever-changing yet persistent across time. The pale sunlight filters through a hazy, mist-laden atmosphere, casting soft, ethereal glows over the shallow seas and emerging continental fragments. Below, the Cambrian sky is different from the one we know today. Clouds are sparser, and their formation is driven by a simpler atmospheric system, shaped by lower oxygen levels and higher concentrations of carbon dioxide. The air itself carries a slightly heavier, more humid feel, dense with water vapor rising from the warm, shallow oceans. As sunlight pierces through this atmosphere, it scatters differently than modern light, giving the sky subtle tints of amber, soft pink, and muted blue. These gentle colors cast a dreamlike quality over the surface, accentuating the vast expanse of oceans and the irregular, fragmented landmasses poking above the waterline top. From this height, Earth appears as a planet defined by contrasts. The deep blues and turquoises of shallow seas intermingle with darker, warsh waters, creating irregular patterns of light and shadow. Sediment-laden river mouths feed deltas that glow faintly under the sun, their murky hues contrasting sharply with clearer offshore waters. Scattered across this watery expanse are pale patches, shoals, reefs, and microbial mats, tiny hints of life concentrated in shallow zones. Though microscopic from this distance, these communities collectively influence the color, reflectivity, and chemistry of the oceans, leaving subtle traces detectable even from a near-space perspective. The land, still fragmented and mostly barren, emerges as scattered islands and protocontinents. These rocky outcrops rise sharply from the seas, forming irregular coastlines that twist and bend under the influence of tides and currents. Without dense vegetation, the continents reflect sunlight differently, creating muted tones of gray, brown, and ochre. Mountainous regions cast long shadows, sculpting the landscape with light and dark contrasts. From space, these fragments suggest the slow, patient work of tectonic continents drifting, colliding, and reshaping themselves over millions of years, yet almost imperceptible to the casual observer. Atmospheric phenomena also shape the visual landscape. Occasional storms form in the warm tropical seas, their swirling clouds visible as subtle spirals when viewed from above. The storms are smaller than the cyclones of modern Earth, yet they carry energy that mixes ocean and atmosphere, redistributing heat and nutrients. Lightning occasionally arcs through these clouds, illuminating distant horizons in sudden, fleeting bursts of light, hinting at the unseen power of atmospheric dynamics. From space, the thin, hazy atmosphere defines the planet's silhouette against the darkness beyond. Earth's curvature is gentle, yet perceptible, framing oceans and continents in a subtle arc. The scattered cloud formations create a soft veil, partially obscuring the waters and land below, while atmospheric scattering imparts a faint, glowing halo along the horizon. The overall impression is of a fragile, emerging world, a planet alive with chemical, physical, and biological processes, yet delicate. Still in the midst of its own formation and evolution, the interaction of light with the ocean's surface adds another layer of beauty. Sunlight penetrates shallow waters, illuminating reefs, microbial mats, and sediment layers, creating shifting patterns of color and brightness. Deeper waters absorb more light, appearing darker and more mysterious, a realm largely unexplored by early life. This interplay of illumination creates a patchwork effect, where life, chemistry, and geology combine to produce subtle textures and gradients visible even from high above. Even the movement of the seas is perceptible from this perspective. Tides, waves, and currents slowly reshape coastlines, redistribute sediments, and mix nutrients. These dynamic processes are invisible to life at the microscopic scale, but have far-reaching consequences, influencing the chemical and physical environment for all organisms. Viewed from space, the oceans appear as living, flowing entities, their constant motion a reminder that Earth is never still, even when life is invisible to the eye, as your imagination hovers above. Notice the faint glimmers that hint at geochemical activity beneath the surface. Hydrothermal vents, volcanic outflows, and mineral-rich upwellings subtly influence ocean color and reflectivity, though imperceptible to the naked eye. These processes are central to the global balance of elements and the sustenance of life. From this vantage point, the planet is not just a physical body, it's a chemically alive system, where every ocean current, every cloud formation, and every sediment layer participates in an intricate, invisible dance. Finally, the overall view from space instills a sense of scale and wonder. Life is small, delicate, and yet deeply interconnected with the chemistry, physics, and geology of the planet. The oceans, continents, and skies form a unified system with cycles and feedbacks invisible yet indispensable. Earth in the Cambrian is both fragile and resilient, emerging from eons of geological shaping and chemical evolution, offering a window into the complex interplay between planetary processes and the earliest flourishing of life. As you gently drift in imagination, let yourself absorb the subtle majesty of this early Earth. The soft, hazy sky, the gently rippling seas, the fragmented continents, and the invisible chemical rhythms that sustain life. From this perspective, it is clear that life and planet are inseparable, co-waving in a quiet, persistent symphony and intricate dance of light, water, air, and living chemistry that has shaped the trajectory of life across hundreds of millions of years. As we hover above the Cambrian Earth, our attention shifts from the broad view of oceans and continents to the dynamic, ever-changing atmosphere. Clouds drift slowly across the pale sky, forming and dissipating in response to heat from the sun, rising humidity, and interactions with the oceans below. Unlike the complex weather systems of modern Earth, Cambrian clouds follow simpler patterns. Yet they are no less important. Regulate temperature, redistribute moisture, and subtly influence chemical cycles across the planet. Observe how the sunlight interacts with the clouds, scattering through water droplets to create soft gradients of color. During the early morning, the sky may glow with muted pinks and yellows, gradually shifting to pale blues as the day progresses. Occasionally, the sun catches the edges of clouds, illuminating them from behind in ethereal, glowing halos. These subtle effects give the Cambrian sky a dreamlike quality, enhancing the sense that this is a world both fragile and alive, where every atmospheric movement has significance. Weather patterns, although simpler than modern ones, play a crucial role in shaping both physical and biological landscapes. Gentle breezes stir the surface of the shallow oceans, influencing the distribution of nutrients and plankton. Currents carry warmth and chemical signals from one region to another, indirectly affecting growth rates and reproductive cycles of marine organisms. Periodic storms develop in tropical seas, their swirling clouds visible from above as faint spirals. These storms, while smaller than today's cyclones, redistribute heat and moisture, mix ocean layers, and create temporary refuges and challenges for early marine life. Lightning, though infrequent, punctuates the Cambrian sky with sudden, ephemeral bursts of energy. Each flash illuminates distant horizons, revealing distant mountains, islands, and the endless stretch of oceans. Beyond its visual spectacle, lightning contributes to the chemistry of the atmosphere, helping to fix nitrogen and subtly influence nutrient cycles. From above, these sporadic bursts of light and energy remind us that even the most fleeting atmospheric phenomena can have lasting effects on life. Below, cloud movements are intimately connected to the surface. Evaporation from warm, shallow seas feeds moisture into the atmosphere, creating local cloud banks that drift with the wind. Areas of open ocean appear darker from space, while regions with dense cloud covers scatter light differently, producing patterns that reflect both meteorology and the underlying chemistry of the seas. These patterns are not random. They are a visible expression of the complex interplay between energy, water, and planetary rotation, a system that governs the habitability of the planet. Occasionally, volcanic activity influences the atmosphere. Ash clouds and mineral particles rise into the sky, creating temporary veils that diffuse sunlight and alter weather patterns. These plumes are visible from space as faint swirling hazes blending with natural cloud formations. They serve as reminders that Earth is not static. Chemical and physical processes are constantly interacting, shaping the sky and influencing climate. Marine life, and eventually life on land, responds subtly to these variations, adjusting behaviors and distributions according to atmospheric conditions. Even the interplay of day and night creates subtle visual phenomena. During early morning or late evening, the low sun casts long shadows across shallow seas, highlighting textures of sediment and reefs below. Clouds catch this longo light, glowing in soft hues that transition smoothly across the sky. At night, the planet's surface is barely visible under faint starlight. Yet the ocean continues its gentle movements, the chemical and biological rhythms persisting even in darkness. From space, these transitions create a gentle, almost meditative perspective of a world in motion, quiet yet alive. The movement of water vapor, clouds, And wind also conveys a sense of the planet's energy balance. Warmth from the sun drives evaporation. Convection carries moisture aloft, and gravity guides precipitation back to the seas. This constant cycling is crucial for life, redistributing nutrients, maintaining surface temperatures, and influencing chemical reactions within oceans and sediments. Even in the absence of complex land vegetation, the atmosphere plays a key role in sustaining ecosystems, regulating the conditions that allow life to flourish. From this high perspective, it becomes clear that Cambrian Earth sky is not just a backdrop, but an active participant in the planet's story. Each cloud formation, each subtle change in light, each gust of wind is linked to the larger environmental and chemical systems. Life below is attuned to these atmospheric rhythms, evolving in synchrony with the invisible currents that sweep across oceans and continents. The sky is both a stage and a teacher, illustrating the delicate balance of forces that make Earth habitable. As your imagination drifts through these Cambrian skies, notice the interplay of light, motion, and chemistry. Clouds rise and fall, storms swirl and dissipate, sunlight scatters across waters and sediments, and the planet hums with invisible rhythms of energy and life. From space, Earth is revealed as a living system, its appearance shaped by the delicate dance of atmosphere, ocean, and light. Every subtle pattern and movement contributes to the long-term evolution of life, reminding us that even the most ephemeral phenomena leave lasting impressions on the course of planetary history. As we drift even higher above the Cambrian world, far beyond the clouds and shallow seas, the Earth begins to reveal itself as a complete, coherent system. From this vantage point, the planet appears as a delicate sphere, a fragile jewel suspended against the dark expanse of space. The oceans dominate the surface, a patchwork of light and deep blues, punctuated by scattered continental fragments and rocky outcrops. Even from this height, subtle variations in color, brightness, and texture hint at the underlying chemistry, life, and geological processes shaping the planet. Notice how the shallow seas reflect sunlight differently than deeper waters. Turbid, nutrient-rich areas glow with muted shades of green and brown, while clearer waters shimmer in turquoise and deep azure. These contrasts are subtle, yet they communicate volumes about the distribution of life, the flow of nutrients, and the dynamic interaction between ocean and atmosphere. Tiny microbial mats, reefs, and early marine communities leave traces that ripple across the surface, visible as faint patterns that shift with currents and tides. From this perspective, even microscopic life contributes to the visual character of the planet. The landmasses are scattered, irregular, and largely barren, yet they define the contours of Earth's surface. Small islands and protocontinents rise sharply from the water, their surfaces reflecting sunlight in muted browns, grays, and ochres. Mountainous regions cast elongated shadows, creating dramatic contrasts that add depth and texture to the planet's appearance. Without the blanket of vegetation we see in later eras, every rocky outcrop and sediment-laden coast contributes to the visual identity of Cambrian Earth, revealing the raw, formative forces of tectonics and erosion at work. The clouds, drifting gently over oceans and land, add a subtle veil that softens the scene. From space, their presence is both protective and revealing. Sunlight glances off their tops, creating gentle highlights and shadows that accentuate the curvature of the planet. Storms, though smaller than today's cyclones, create swirling patterns, a visual manifestation of energy transfer between atmosphere and ocean. Lightning occasionally punctuates these formations, brief flashes illuminating distant horizons and offering a glimpse into the unseen chemical and electrical activity that shapes the environment. Below, Earth's atmosphere forms a thin, fragile halo along the horizon, a glowing rim that separates the planet from the infinite blackness of space. This halo, tinted by water vapor, carbon dioxide, and other gases, demonstrates the subtle complexity of the Cambrian sky. Its thickness, composition, and refractive qualities influence how sunlight scatters across oceans, land, and clouds. From above, this atmospheric layer conveys both beauty and vulnerability, a delicate interface that mediates the conditions necessary for life, time, and motion. Add another layer to the visual experience. The planet rotates slowly beneath us, creating shifting light and shadow across oceans and continents. Cloud patterns drift, storms evolve and dissipate, and currents ripple across the surface. From this vantage point, we witness not only the static form of Earth, but also its constant, dynamic change. Every movement is a reflection of energy, flow, chemical interaction, and physical processes invisible from the ground, but vividly apparent from space. Even subtle geochemical and biological processes leave marks visible at this scale. Nutrient-rich waters shimmer differently than barren regions. Volcanic plumes create faint veils of haze, and sediment deposits in shallow seas subtly alter reflectivity. These patterns reveal the invisible activity of the planet, hinting at life, chemistry, and geology interacting in real time. The Cambrian Earth is alive in ways that transcend individual organisms. Its surface, atmosphere, and oceans form an interconnected system that evolves and responds to internal and external forces. As observers, we gain a sense of scale and fragility. Life is small and delicate, yet deeply entwined with the planetary system. Every storm, every cloud, every current affects the chemistry and habitability of the seas below. From this distance, the relationship between life and environment becomes clear. Organisms adapt, migrate, and evolve in response to forces too large for any one species to control. Geology, chemistry, and climate dictate the canvas upon which evolution paints its intricate and enduring patterns. Finally, let yourself linger on this vision. Earth in the Cambrian is a planet of contrasts, vast oceans, and scattered lands. Calm skies and sporadic storms, fragile life and relentless environmental forces. Viewed from space, it is a symphony of light, color, motion, and chemistry, a world in quiet but constant transformation. The appearance of the planet reflects its history, its processes, and the invisible stresses that have guided life since its earliest days. From this perspective, we appreciate both the beauty and complexity of a young Earth, a living, breathing system poised for the evolutionary adventures that are yet to unfold as your imagination drifts further from the planet. Remember that this perspective, seeing Earth as a whole, dynamic entity, offers more than visual splendor. It conveys the interconnectedness of life and environment, the invisible influences of chemistry and physics, and the patience of a planet shaping life over hundreds of millions of years. In the Cambrian, Earth is both teacher and stage, revealing the subtle and profound ways in which the appearance of a planet reflects the hidden rhythms of life. Beneath its surface, as we float above the Cambrian Earth one last time, a gentle sense of completion settles over both the imagination and the mind. The oceans are calm, reflecting the faint remnants of sunlight, while continents rest quietly beneath the soft embrace of drifting clouds. Life continues, its slow, deliberate dance. Microbial mats shift subtly. Tiny grazers glide across the seabed, and currents carry nutrients steadily through the water. Everything moves with a natural, unhurried rhythm, and in this rhythm, a profound serenity emerges. Take a moment to let your mind sink fully into this calm. The Earth itself seems to exhale a slow, measured breath encompassing seas, skies, and land. Each ripple in the water, each gentle shift of sediment, each soft flicker of light across shallow reefs contributes to a harmonious pulse. There is no urgency, no pressure. The planet operates with timeless patience. Allow this ancient cadence to soothe your own thoughts, letting tension fade and awareness rest gently in the present moment. Notice the subtle sounds of this imagined world. The whisper of currents brushing against the ocean floor, the faint rustle of plankton drifting in slow motion. The gentle sigh of wind over distant landall form a natural lullaby. Even in the absence of human ears, the imagined soundscape creates a sense of calm that permeates the mind. Let these sounds mingle with the visual serenity, forming a complete sensory immersion in tranquility. From above, the scale of the planet is humbling. Oceans stretch infinitely. Continents seem both vast and delicate. And life moves persistently, yet quietly, weaving an intricate web of interactions. Each small organism, each minor current contributes to the enduring balance of this world. The lesson is clear. Beauty, harmony, and resilience often exist in subtle, almost invisible ways. It is not the grand gestures, but the continuous, measured actions that sustain life over millennia. As night falls over the Cambrian seas, the colors soften into muted shades of deep blue and gray. The last traces of daylight vanish, leaving a gentle darkness that encourages reflection and rest. Clouds drift lazily, breaking occasionally to reveal faint glimmers above, and the oceans mirror this quiet glow. Life continues, patient and steady, guided by rhythms older than memory, a testament to endurance and balance. Let yourself become part of this rhythm, breathing with the pulse of the planet, letting each inhalation and exhalation align with its calm continuity. Consider the lessons this ancient world imparts. Patience and persistence allow life to thrive. Interconnection and diversity foster resilience. Subtlety and quiet action can shape the course of ecosystems across millions of years. The Cambrian Earth is both teacher and companion, inviting the mind to rest while absorbing its wisdom. By attuning to these lessons, we find not only wonder, but also peace, a quiet reassurance that existence itself can be gentle, continuous, and profoundly beautiful. Finally, as we prepare to leave this ancient Earth behind, imagine the planet slowly fading into the distance, its rhythms continuing undisturbed, its life persisting in calm harmony. Carry with you the tranquility of its oceans, the serenity of its skies, and the gentle persistence of its earliest life forms. Allow these sensations to settle deeply within your mind and body, guiding you toward rest, reflection, and a lingering sense of awe. The Cambrian Earth, with its timeless cadence and gentle patterns, offers a perfect close to our journey. It reminds us that life's continuity, the balance of ecosystems, and the subtle rhythms of the natural world endure far beyond any single moment. Let this understanding bring a lasting calm, a deep sense of connection, and a peaceful conclusion to your evening, as your imagination drifts further into stillness. Feel the gentle flow of life across oceans and continents, the subtle interplay of currents, clouds, and organisms, and the quiet, enduring beauty of a world 500 million years in the past. Here, in this serene, ancient landscape, the mind can rest, the body can relax, and the soul can reflect on the wonder of life itself. With this final vision, our journey concludes. Cambrian Earth continues its silent dance, timeless and untroubled, leaving us with lasting lessons of resilience, harmony, and calm. Let these impressions linger, carrying you gently into rest, reflection, and the quiet joy of having witnessed one of the earliest chapters of our planet's grand story.